Welcome everyone to the fall 2021 SpecNet Community Meeting. Just a few items with logistics here. So this meeting is being recorded. It will be made available on the newly created SpecNet YouTube channel. Right now it's this big URL here. We're going to post this in the chat and in the website. You will be able to find this easily. For the organization of the sessions, we will have longer talks and shorter talks, and we'll have a short Q&A session right after each talk. And you can use the chat function to pose questions at any time, and we will have a longer discussion at the end as well. We also set up this a little poll for us to gather some feedback from you. The idea with this poll is for us to select what will be the breakout rooms in the end. So this is something new that we're trying out to try to make this a little more dynamic. And as you see interesting things during the talks, you might have an idea and want to chat with the speaker or with some of the participants a little more about that. So you can add your question there. And you can also vote in the proposals that are there, and the questions that are there. So the most voted questions, and this is an odd format. It's not really a question. When you go to the Q&A function on this tool here, you just add a question, but this is a suggestion for a breakout room. And you can also vote on the suggestions that other folks have in there as well. So in the end, we'll try to make these suggestions, these entries in the Q&A, part of the breakout rooms that folks can join. We also have live transcript enabled. You can enable that in your Zoom interface. This is an automated generation for transcript subtitles. So it's not always perfect, but it can be helpful for some folks. So feel free to use that as well. And now I will hand over to John Gammon to do the introduction for the meeting. John?
Thank you, Gilberto. Welcome, everybody. Can you see my screen?
Yes, looks good.
Okay. All right. Well, welcome to everybody. I see some old friends from SpecNet, old meetings, and lots of new people. So welcome to all. And for those of you who are not familiar with SpecNet, I wanted to say a little bit about the purpose and history of SpecNet and today's science themes linking spectral measurements to fluxes and scaling. Okay, so a bit of history first. We began in 2003 as a working group at the National Center for Ecological Analysis and Synthesis in Santa Barbara. It was smaller groups than we have today, and some of you were there. We put out a special issue of Remote Sensing of Environment. In 2012, we transitioned to a nonprofit, and we've done things like start a small grants program, which you might be interested in. Also, the purpose has remained essentially the same, which is to advance collaborative science and technologies integrating flux measurements and remote sensing measurements. When we started this, the idea of doing remote sensing in conjunction with flux measurements was a bit of a new idea, particularly the idea of proximal remote sensing. So a lot of what you see in the right is sort of a cartoon to show some of the kinds of things historically that people have done. I left the blimp in because actually people were using blimps back there. This is really before the advent of cheap commercial drones, so things have changed. But the basic themes are the same, which is when you try to compare remote sensing to flux measurements on the ground, you have challenges. Flux measurements measure one point in space through time continuously, whereas remote sensing often is a snapshot that you might have it repeated, but it doesn't have that same continuous sampling, and it's at a different scale, often very coarse scale. So the idea was by adding optical sampling tools, technologies on the ground or near the ground through time, we could better link these things, remote sensing to flux measurements. So people have done all kinds of things historically. You know, you can walk around, you can mount things on towers, put them on robots, fly drones, all sorts of technologies. And this is one of the interesting things and one of the challenges within this group. Basically, I like to think of SpecNet as the glue between remote sensing and flux sampling. And it also ties, because it's at proximal scales, it ties to the measurements we might make in the field, ecology, physiology. So it kind of helps tie all these things together. It's not as simple as this, as we will talk about today. And as you'll see in this slide, just take the example of scaling and photosynthesis as an example. Everything here in this picture is a depiction of how we might measure photosynthesis optically here, or with other kinds of remote sensing methods, fluorescence, reflectance, thermal methods, all are relevant. And here's some ways we might measure photosynthesis or fluxes. And these are space scales and time scales on log scales, and basically showing that at this scale down here, we measure things one way, but up here we might measure them a rather different way. And you can see all the different tools that people use. The basic point here is that even if it's the same process, it is measured differently, and there's emergent properties at every scale that affect how we can see things or how we can measure them. And even our language that we use changes with scale. We might call it photoregulation at the fine scale, or photosynthesis at the leaf scale, or net primary productivity, or gross primary productivity, or surface atmosphere feedbacks. So we span all of this when we try to link remote sensing to flux measurements. So all of that are the themes for today. Welcome. We're glad you're here. Thanks for putting up with us on this new format that we're trying out. And I want to give a particular thanks to the board members here, Troy, Yuki, Gilberto, Fred, Lauren, and Danette, who have made this meeting possible. And I guess one last thing is if you need some directions, you can go to the SpecNet website, specnet.info. And if you go to the About tab, you can find the schedule posted there, as well as other information about SpecNet. So that's all I have to say, and let's continue. I think Yuki is going to introduce our first speaker.
Yes. Okay, so the first session have 5 talks. So before break, so first speaker is Dr. Miriam Johnson. And Dr. Johnson defended her doctoral thesis earlier this year. Is that correct? Yeah, yes. Congratulations. She has conducted in-depth research on patterns of vegetation temperature that influences various aspects of ecosystems. So she recognized that the challenges in measuring the vegetation temperature at ecologically meaningful temporal and spatial scales, and this limits our understanding of spatially exclusive thermal patterns, as well as evaluating surface energy balance in ecosystems. So her talk today is titled Proximal Thermal Sensing. So we are looking forward to learning about your research. Thank you.
Thank you very much. Can you see my screen all right?
Yes.
And can you hear me and see me?
Well, I can see your screen. Yes. I can hear you.
All right, perfect. All right, well, thanks very much for the introduction, and thank you very much for having me. I'm going to turn on my timer here before I forget. I'm going to talk about thermal remote sensing today, and I'm going to try to touch on both themes of this conference, both scaling from ground to satellite and also linking with fluxes, and then I've added models. I did most of this work as part of my PhD at Harvard in Paul Moorcroft's lab, and right now I'm a postdoc at the University of Iowa with Matt Dannenberg. And I'd like to begin just by motivating why plant temperature is awesome to study. It's interesting and important. First of all, it's really fundamental in defining carbon fluxes. So here's photosynthesis rate on the y-axis and leaf temperature there is on the x. The different panels are different species, and the different lines in each panel are growth temperature. But you can see that kind of regardless of species and growth temperature, there's this really characteristic and really strong relationship between photosynthesis rate and leaf temperature. Here's the other half of our carbon flux, respiration rate. Leaf temperature, again, is on the x-axis. And the top panel is showing the relationship between various biomes and leaf temperature. and various plant functional types, and leaf temperature in terms of respiration. And you can see that taken together, temperature has a huge impact on both photosynthesis rate and respiration. Of course, temperature is also really important for water dynamics. So here now, again, leaf temperature is on the X and transpiration rate is on the Y. And this is a very busy plot because tons of stuff influences transpiration rate. But if you just follow my sort of wiggly blue highlights here, that is the expected influence of leaf temperature on transpiration rate, all other things being equal. And you can see, again, leaf temperature plays a huge role. Leaf temperature is a very cool indicator of a lot of stuff we might be interested in ecosystems. So here's a neat paper where they were imaging tobacco leaves, and on the left side are thermal images, and on the right side are sort of RGB or visible images. Row 1 is time point 1, row 2 is time point 2, and you can see that tobacco mosaic virus, with which this leaf has been infected, is visible in the thermal range before it is visible in the visible range, which is pretty cool. Very similarly, here is a leaf. It's been chomped on by this hot larva. And you can see that the places where the leaf has been chomped are warmer. Places where the leaf is damaged are warmer than the other parts of the leaf. And at a bit of a larger scale, here's the soy face experiment. And inside this large quadrat, there is CO2 enrichment. And so the soybean plants inside have closed their stomata relative to the plants on the outside. And you can see that these internal plants are much warmer because of that than the external plants. In visible imagery, this would look very, very similar inside to outside. And finally, at really large spatial scales, surface temperature and plant temperature, because of course plants cover much of the surface, is a really fundamental control on surface radiation balance, because everything is radiating according to its temperature. So a warmer surface will tend to have a higher long wave out term here, and will play a pretty big role in defining sort of the energy in the terrestrial system that is available to do stuff. In addition to plant temperature being great, this is a really good time to start thinking about it and to be doing research in thermal biology, because thermal remote sensing data are increasingly available. And when I say remote sensing, I'm defining that at multiple scales. I think it applies to both proximal thermal sensing, which, for example, would be like a camera on top of a tower. Here's an example data image from a proximal thermal remote sensor, and also satellite thermal sensing. And there's also some airborne sensors, of course. So this is an image from EcoStress. EcoStress was launched to the International Space Station in 2018. Some really, really cool science coming out of EcoStress. And we can also expect that thermal remote sensing is going to be a priority in the future with the SBG mission. So excited about that. All of the work that I'm going to introduce in this talk has been done at the Tonzi Ranch Ameriflux site near Ione, California. And here at the beginning, I just want to shout out to the Baldacci group who manages this site, and also we're collaborators on this research. It's a wonderful place to work. It's a wonderful group to work with. So thank you to the Baldacci group. The Tonzi Ranch Flux Tower is here in the center of this 1 by 1 kilometer area. And it is in what is affectionately, I think, called the Blue Oak Bathtub around the Central Valley of California, sort of in the foothills of the Sierras. So here's what it looks like on the ground. These are blue oak trees, Quercus douglasii, and this is an example of a blue oak leaf in close-up. And then the understory is annual C3 grass. And this image was taken in the dry season. So the grass is sort of crunchy and brown and not doing much, whereas the trees have leaves. It's a Mediterranean system, so the summers are hot and dry, the winters are cool and wet. With that introduction, I'm going to leap right into the first theme of the conference, which is scaling from ground to satellite. And I'm going to talk about this in the context of comparing thermal camera measurements with EcoStress acquisitions at that site in Tonzi Ranch. And I'd like to be clear here at the outset that I'm not especially trying to evaluate which of these things is better, the thermal camera versus EcoStress, but more acknowledging that they're both data sets that can be incredibly valuable, and therefore it would also be incredibly valuable to understand how they're related to each other and how to combine them. Of course, in reconciling camera and satellite data, spatial mismatch is a challenge. Dr. Gaiman just mentioned this, and I think we're likely to hear a lot more about this as the day goes on. So the thermal data sets, again, look kind of like this. The camera is mounted on a tower. These far trees are something like 200 meters away. And in my case, the lens was a 45-degree lens, so 45-degree view angle. And so the camera is viewing something that looks kind of like this pizza slice from about 18 meters high. In contrast, the ecostress sensor is viewing this latitude, usually at approximately nadir. This is the 1 by 1 kilometer area that matches this aerial image here. And you can see that there are some pretty obvious challenges that might be associated with trying to reconcile something that looks like this with something that looks like this. Of course, the extent of the ecostress image I'm interested in, and I'm interested in this extent because it matches up pretty well with the flux tower footprint, but also the size of the pixels here in ecostress versus the comparative high resolution here in the FLIR thermal camera. One major conclusion from this scaling study is that ancillary data are really, really useful. This will probably also surprise nobody. So the first ancillary data set we used to try to match up these two different kinds of data was an Iconos image. Here it is on the left side. It's relatively high resolution. Here it's at 1 meter. And I've stretched it so that you can see that the oaks are sort of more greeny and the pines are more bluey. But what we did was we classified that image into grass, oak, and pine, and of course, masking out the road and the pond and other non-vegetation things. We then brought in a LiDAR data set at this site, and we made a digital surface model based on that LiDAR data set, which you can think basically as laying a sheet over the entire landscape. So the digital surface model, it includes both the elevation and the height of the tree. And then with information about where ecostress was at every overpass, and also where the sun was at every overpass in terms of the angles to the ground, we actually made a hillshade for every single ecostress overpass across the entire 1 by 1 kilometer study area. Combining that hillshade with the vegetation classification, we can say what the proportion oak, pine, shaded grass, and sunlit grass was in each ecostress pixel at the time of overpass. Then we did something pretty simple. Basically, knowing the fractions of all those types of vegetation cover in each pixel, we defined end member energies of each of those vegetation types using the FLIR image. So these blue polygons are oaks, the green polygons are grass, and the white polygons are pines. We took the temperature from those FLIR images, defined the end members, weighted them accordingly, energy, not temperature, because they don't scale linearly, and essentially created a FLIR image that looks in spatial resolution quite like the ecostress image to compare them. What we found was kind of interesting. So here, if you just look at the left panel for starters, I'm showing ecostress temperature on the Y and FLIR-based temperature on the X. The cyan dots here are mean scene temperatures, and the colorful dots around them are colored according to incoming shortwave radiation at the time of acquisition, and they're per pixel within the scene. And what you can see is that at low light, so down here mostly, and a little bit of this purple, there's relative agreement between ecostress and FLIR. And again, when I say agreement, I'm not necessarily judging one to be the evaluator of the other. The root mean squared error of the mean scene temperature at night was less than a degree. That's well within the camera's margin of error. And if you take it at the pixel scale, it was about a degree. In contrast, at highlight, ecostress is consistently warmer. And so this is interesting, and it helps us to start to think about how we might do the scaling better, or what ecostress is seeing that's different from the FLIR. One possibility for this discrepancy at highlight is the ecostress geolocation error. So I expect it's maybe plus or minus 50 meters, which is kind of big. You would expect that geolocation error would yield relatively higher errors at times of highlight, because that's when the surface is thermally heterogeneous. So if we don't know exactly what ecostress is pointing at, but all of the surface kind of looks the same, it doesn't matter. The converse is also true. That said, if it really were a geolocation error issue, I would expect that there'd be sort of like a funnel of error around the 1-to-1 line, sometimes too hot, sometimes too cool. That's not really what we see. And so I think that the more likely explanations for this disagreement between the sort of camera type scene and the ecostress type scene are one of these two or some combination. Our digital surface model, that sheet, is in fact opaque. So it's very likely that we actually overestimated shade because the trees themselves are fairly sparse. Also, it's possible that ecostress sees soil in addition to grass, and I know in reality that soil gets much warmer than the grass. So in summary, just wrapping up that first section, I would say that understanding how proximal and satellite thermal remote sensing correspond is both a priority and a challenge, especially a spatial scale challenge. Data fusion, LiDAR, high spatial resolution, visible imagery, probably a bunch of other stuff is incredibly useful when we're trying to reconcile these two scales of data. And for our particular application, temperature measurements were more comparable at low light when there was less thermal heterogeneity as expected. And with that, I'm going to jump right to the second theme, linking with ecosystem fluxes. And I've added and models because my PhD lab worked a lot on a model, as did I. And I'm going to talk in this section about evaluating a terrestrial biosphere model with thermal remote sensing data and how valuable combining the remote sensing data with the flux data is when you're trying to diagnose something as complicated as an ecosystem model. The model that I worked with was the ecosystem demography model, ED2. And here I'm just showing you that ED2 represents variability in horizontal space. So here, for example, is a modeled patch of ecosystem. It has, a tall dark tree and a mid-sized light tree. You can think of them as pine and then underlain by oak and then a layer of grass and some soil layers. The next door patch might be different and the next door patch might be different than that. So in that way, ED2 is representing light heterogeneity and vegetation heterogeneity in the ecosystem. As major inputs, it takes meteorology and soils and an option to take phenology and initial condition. I wanted my simulation to be as close to this particular site as possible, and so I did use those options. There are tons of equations, and all of those equations have parameters, of course, and then it outputs carbon, water, and energy fluxes, which could be compared to flux data from towers, and also plant demographic information, growth, mortality, and recruitment. And sort of improving these models is an all hands on deck kind of exercise in terms of the data that are useful. And this is what I mean when I say that flux data and remote sensing data really work together here. So ED2, like many of the terrestrial biosphere models, conserves quantities, by which I mean the energy budget is closed, the carbon cycle and the water cycle are closed. And you can think of that as kind of the correct amount of air in this balloon. But the balloon doesn't start to look like a balloon animal until you start to put twists in it. And bringing different data sources to bear is quite like putting twists in your balloon animal. I'm jumping right to results here for the sake of time, but I'd be delighted to talk about methods in questions or after, or email me. So here, these plots look similar to what I've shown in the past with the ecostress FLIR comparisons. Now ED2 temperature, so predicted surface temperature, is on the y-axis. The first panel has ecostress temperature on the x, and the second panel has FLIR temperature on the x. And again, the cyan dots are the mean seen temperatures, whereas the cloud of colorful points around them is colored by incoming shortwave radiation. It's a linear scale, and those are the individual pixels. And what we see is that ED2 temperature is a bit warm. On average, it's 3.1 to 3.3 degrees warmer than measured. And you might think, based on the prior project that I was talking about, that that would be a day-night thing. And it's actually not surprising to me. So ED2 minus ecostress temperatures, these are mean seen temperatures in the day, were very comparable to the differences at night. And the same was true in the comparison between ED2 and FLIR. What the mismatch is absolutely associated with is wet season versus dry season. So here again, we have the difference between ED2 and ecostress and the difference between ED2 and FLIR. They're in opposite directions. This is not surprising given that ecostress and FLIR don't always agree. In the wet season, ED2 is almost spot on. Given how many equations are in this model and the fact that temperature is not a prescribed variable, that's a predicted variable, this blew my mind. In contrast, in the dry season is where the discrepancies really occur. The proximal thermal remote sensing allows us to get more specific than that. So rather than just looking at pixels now, we can look specifically at oaks and at pines and at grass and soil, which is really cool because in ED2 world, we're omniscient. So we know all the information for everything. So here I'm showing 2 boxes in 5 different months, some wet season months and some dry season months. The light boxes are the predicted temperatures and the dark boxes are the FLIR measured temperatures. And this, again, blew my mind. In April and May, the mean daily measured and modeled average temperatures were within a degree Celsius. Wow. In contrast, all modeled plant types were warmer than measured in June and July, and especially the modeled grass. And that significant grass soil difference, as notated by these asterisks here, persisted throughout the summer. All right, so now it's time to start thinking about why this might be, why the discrepancy exists and how we might be able to rectify it. And I'm gonna ruin the punchline by saying that my hypothesis here is that the ED2 model requires an energetically resolved litter layer to model dry season surface temperature with fidelity. So what do I mean by that? Well, at the site, dry season kind of looks like this. So there's some soil visible, but for the most part, there's this layer of dry, crunchy grass sitting on top of the soil. In the model, though we resolve litter in the carbon cycle, we do not energetically resolve this litter. So in the model, from the energy perspective, this scene actually looks like this, where there's bare soil. I know because the FLIR, the camera, allows me to distinguish the soil and the grass temperature, that bare soil gets much, much warmer than dry grass litter, especially in early summer, by an average of about 4.5 degrees, but with quite a lot of range. That magnitude's pretty comparable to the magnitude by which ED2 grass temperature is too warm. So here's the sleuthing part, trying to figure out, whether this hypothesis is promising or not. And there's where the flux tower data comes in. So here I'm showing latent heat flux on the Y, and it's a time series. The ED2 predictions of latent heat flux are these solid lines, and the Ameriflux measurement are the dotted lines. And I would like to draw your attention to these funky points here, these peaks that the model predicts that the measurements by and large do not show. Again, because I'm omniscient in ED2, I happen to know that that's attributable to evaporation at the beginning of the wet season, like a strong pulse of evaporation. And that literature suggests would be attenuated by the presence of litter. Here's sensible heat flux. So ED2, again, is the solid line and Ameriflux is the dotted. You can see that ED2 sensible heat flux generally doesn't peak as high as it should. Again, this is supportive generally of the litter hypothesis because grass litter would be a relatively more efficient convector of sensible heat than that bare, smooth soil.
Miriam,
Yeah.
a couple, 2 minutes, 2 to 2.5 minutes.
All good. And then this is a measurement from the top of the flux tower, not a flux measurement per se, but here's net radiation. You can see that ED2 net radiation is low compared to Ameriflux measured net radiation. And here I'm just decomposing the net, which is in the dark colors, into shortwave in blue and long wave in green. And you can see that the net discrepancy is mostly a function of long wave discrepancy and not shortwave discrepancy. And that makes sense because surface temperature is too high in the model. And here's the kicker. If I force the model to keep grass leaf area index high, so instead of saying in the dry season model, you have soil under your trees, now I'm saying in the dry season model, you still have grass, that net radiation fixes right up. And the model data net radiation comparison is much improved. So that's the difference between the black line, which is the same as it was up here, and the red line, which is when I turn off dynamics. In other words, I force grass LAI to stay high. So in summary here, the combination of remote sensing data, both proximal and also satellite, and flux data is incredibly valuable for model evaluation. And for our particular application, our model is capturing wet season absolute temperatures quite well, predicts several degrees too high in the dry season. I didn't show you much data about plant temperature response to environment, but I can tell you it looks pretty reasonable. And an energetically resolved litter layer is a development priority for us. And with that, I would like to thank funding sources, which are my PhD department and also NASA, and my collaborators on this study, Paul, my advisor, and also the wonderful people at UC Berkeley and Dennis Baldacchi's group. This is my email. Please use it. I would love to hear from anybody, everybody. Thanks.
Thank you, Miriam. This is a very interesting study. Let's see if there are any questions from audience.
There's a couple questions, one directly to Miriam, one to everyone from Fred. Fred's question, does ED2 model aerodynamic mixing within canopies? Does it model aerodynamic mixing within canopies, particularly for the grass layer?
For the grass layer, no. So so canopies, individual canopies in ED2 are infinitesimally thin. So we do have vertical heterogeneity in that you can have a tree canopy over another tree canopy over a grass layer, but we do not have within individual canopies, we don't have mixing. There is, Beer's law is in there, so there's light attenuation and that sort of stuff, but the individual canopies per cohort are very thin.
We have some more questions. Do we have time, Yuki, or should we move on?
Maybe one more question.
Okay, Dave Bowling has a question. Do you correct the flare temperature for water vapor?
Yes, absolutely. Yeah. So we generally follow the Albrecht et al. Temperature corrections to get from what the flare sort of spits out to an actual temperature. We correct for water vapor, we correct for air temperature, we correct for reflected temperature, which is a big one, and for emissivity, which we actually measured with the emissivity box. It was pretty fun. And yeah, so the Albrecht et al. Corrections, and then I have a recent paper out that suggests how we maybe should extend some of those things to open canopy ecosystems where there are a few more considerations. But yeah, that stuff is really important.
That's great. So Miriam, do you think you could kind of post the link to that paper possibly?
Yeah, sure. In the chat?
Yeah, great. In the chat, or chat so that people can take a look at it. Thank you so much, Miriam. That's a very interesting talk.
Thank you very much for listening.
Okay, so the next speaker is Mr. Paul Neff. And for the past 3 years, Mr. Neff has been working on a project called M-Drone for Rivers, so at the JB hyperspectral devices in Germany, and investigating dynamics in riverside areas. His research interest is application of field spectroscopy for remote sensing of vegetation, and he's currently pursuing his PhD at University of Bonn, Germany. The title of his talk today is Using Mobile and Stationary Field Spectroscopy to Investigate Dynamics and Inform Classification of Riverbank Vegetation along Germany Federal Waterways.
Hello, everybody, and many thanks for the introduction. Let me share the screen with the presentation real quick, and I hope that you can see it all. Is that the case?
Yes.
Good. So, yes, in the past 3 years, I was working in this project already introduced in Germany, and we were primarily interested in monitoring the riverside areas of the German waterways. And this falls somewhat in the direction of the scaling question in this meeting. And I think it's really interesting how bring together in situ knowledge of the traditional field work, really with a clipboard to know which kind of plant you find in which location, and then bridging this knowledge with modern sensors, with hyperspectral measurements on the ground, with multispectral cameras on drones and on manned aircrafts. And in the end, I think this can be all very important to use the data, for instance, to inform models, as we've seen in the previous talk. And they learned that this can be really crucial to learn some new insights. With this, I'd like to spread word about JB Hyperspectral. I think most of you who know JB Hyperspectral know us for building the FLOX, the fluorescence box, as a hyperspectral instrument to monitor chlorophyll fluorescence as a proxy for photosynthesis. And our second product, which is much smaller, is the reflectance box, the ROX. And it is commonly used, as the name indicates, for reflectance monitoring. And this was the case also within the frame of this project. So there, the ROX field spectrometer was used on the ground, and in the right panels of this slide, you can see on the top some reflectance recorded over 9 reference panels, which we used as a reference target, so to speak, to cross-compare the other sensors within the field. You can see the equipment, by the way, in the top left in the photograph. And this was brought together with a multispectral camera, which is customly built by the University of Applied Science in Koblenz in Germany. And this was used at the gyrocopter, which you can see at the second picture. And the third sensor, which was used in the study, was the MicaSense Red Edge, which is like pretty much a stock sensor that many of you may know. And all of those sensors, of course, we try to bring together using the reference targets in the field. And starting out with the ROX equipment on the ground, I'd like to introduce, first of all, our stationary application of this instrument. And this was used in 3 locations, basically, to perform long-term measurements. And the idea was to monitor seasonal dynamics of vegetation and sediments as well. So you can see in the first location was primarily set up to monitor near shore dewberry, so vegetation. And in the second location, we were monitoring sediments and pioneering vegetation. And in the third location, primarily pioneers. All 3 setups were solar powered and fully autonomous, and also using remote data transfer. So in principle, we could always see the instrument vital data and also investigate what is currently going on site without needing to disturb these areas too much. And actually, 2 of the instruments were set up in environmental conservation areas. So there was also this requirement to fulfill, basically, to not disturb too much. And we were recording seasonal events and also trends. And I'd like to show you some data from this little exercise. This is a time series which was recorded in the first setup, which I've just shown at the island Nonnenwert. And I think what is really interesting to follow here is the dynamics, and not surprisingly, following a seasonal cycle. So we were starting a little late, not like catching the greening up in spring too well, actually missing it, and then starting with the vegetation canopy fully developed, but recording a nice impact of a heat wave in the red circle that you can see there. And then, of course, this data can be further analyzed with models and fitting some smoothing spline and investigating the vegetation cycle. And I think this is something which we will continue and also investigate this time series to more detail, as is the current state. To move on, the second case of application was the mobile field measurements. And for this, we were using, again, a ROX, which was powered with a battery. And for this mobile application, set on a tripod with an active gimbal to automatically level the optics and ensure high quality measurements. And the tripod allowed measurements up to 2 meters above the ground. So we could, yes?
Two more minutes.
Okay, thank you. So we could measure like vegetation in like medium height. These mobile measurements allowed to record like typical reflectance signatures of vegetation, of which I have 2 examples here for you. First, the dewberry, and then the second, a willow, in multiple locations measured and with a varying field of view, including also a little bit of soil. So what was this good for? We built up a processing chain for this project to actually process the raw data from level 1 to calibrated radiance and reflectance in level 2 to a specific data product, which I call level 3 here. So including some overview table, processed reflectance, and also some multispectral sensor simulation. This all bringing together the metadata in the field. For example, here we recorded a water mudboard in a specific location. And at the bottom right, you can see the derived multispectral reflectance out of the hyperspectral bunch of measurements. The first case of application for this, for us, of course, was the classification and verification of this classification. For example, one of the big problems there is invasive species, and detecting neophytes is very interesting in this context for us. And the second application of this would be the calibration and validation of the aerial images. I think actually should be the most important one, because with this, it's also important to validate the classification. One last thing to mention about this, we have currently a manuscript submitted. So yeah, if you like, I can keep you updated about this process and how the review hopefully is treating us well. And with this, I'd like to thank for your attention. And if there's some questions, I'm happy to answer.
Thank you, Paul. So let's see, one question, if there's anything posted on chat.
I have a question, which is, these technologies help solve a longstanding problem in our community, which is how to standardize on technology, because it's always changing. Do you have any comments on that?
Yeah, this is a big challenge indeed, because the technology in one way is, as you mentioned, is always changing. And I think the principles behind are sort of steady. So, for example, we know that reflectance is a function which is derived with respect to incoming light. But incoming light changes throughout the day. And today it is still a common practice to retrieve, for example, with multispectral cameras, reflectance, which is calibrated with respect to one point in time. And this introduces error, for instance. So a calibration and validation should also respect this course or this changing incoming light throughout the day, for example. I hope this answers your question.
Yeah, thank you.
Thank you very much, Paul. Next speaker is Dr. Samuli Juntila. Dr. Juntila is a postdoctoral researcher at the University of Eastern Finland. His research interest is movement of water within the soil-atmosphere continuum using remote sensing techniques. The title of his talk today is Simultaneous Measurement of Leaf Gas Exchange and Water Content.
Okay, thank you for the introduction. Yeah, so my name is Samuli Juntila. Good evening from Finland. My background is more in remote sensing and forestry. I graduated from the University of Helsinki and now working as a postdoc there in the University of Eastern Finland. I won't be going too much into detail about the background or importance of water in plant physiological processes. You probably are all very well aware of those, and so let's get into it. So measuring plant water status has been quite tedious in general. Still, mainly the main method is measuring leaf water potential with pressure chambers or relative water content, which are all related to leaf water content. But it's very tedious to measure. Water is kind of very slippery. It evaporates or transpires very quickly after removing a leaf. So like getting the even very precise reference measurements for remote sensing can be quite difficult. Water absorbs light energy in the shortwave infrared region very efficiently. In remote sensing, the leaf water content is usually measured as equivalent water thickness, so the amount of water per leaf area. And here in the figure, you can see a leaf reflectance modeled using the Prospect 5 leaf reflectance model at very extremes of different leaf water contents while keeping other leaf parameters constant, and you can see that there's a lot of variation beyond 1000 nanometer and more. But there are other factors that are also affecting these similar regions that water is sensitive to or causing absorption. Leaf mass per area on the left top corner influences these regions as well, and more than that, the kind of on the left lower corner, this kind of leaf structural parameter, which is dimensionless parameter in this model, but you can see that there's a lot of variation in the similar wavelengths. So my interest now is how to get really accurate measurements of leaf water content, and maybe we could have some other kind of approach to it. I've been now using these small hyperspectral sensors, which are made by spectral engines. So you can see they're really small, quite affordable. There's a few different models and options that have different wavelength regions. I have 3 of these that are in the wavelength regions that are mentioned here in the text. So these all are quite suitable to measure the changes in those regions where water is affecting the reflectance. They have programmable wavelengths. You can adjust what wavelengths you want to measure. They have their own lamps, and it's kind of this in-gas type of sensor. They are not spectrally very high resolution, so the full width at half maximum is from 13 to 28 nanometers, usually higher, going to higher wavelengths, and the signal to noise ratios vary quite a bit. The model having the longer wavelengths from 2000 to 2450 nanometers has 1500 signal to noise ratio, which starts to be pretty bad compared to the other 2 models. So I've done some destructive sampling with this. So I sampled silver birch leaves, and using the kind of traditional method used in remote sensing. So taking the leaf out, measuring its reflectance, and then measuring the water content, leaf area, and also the saturated leaf water content to get the relative water content. And looks fairly good, but taking into account that these leaves were also drying in the air, we can get an root mean square error of a bit less than 5 for relative water content, and for equivalent water thickness, it was at the best, it was a bit less than 3.5 grams per square centimeter. And if we think that birch leaves have generally equivalent water thickness in the range of 115 to 100, it means that we are not very accurately able to measure the natural variability in those leaves. But been other tests with this. So how about if we continuously measure the changes in spectral reflectance? And here I was measuring a quite ordinary houseplant, indoor houseplant, Rakaena marginate. A single leaf was measured for a couple of weeks from mid-March till 8th of April. The blue lines depict the watering times, so you can see quite nice, like a diurnal variability. The black is the change in spectral reflectance, or it's a normalized ratio index of 2 wavelengths. But anyway, you kind of see the red is temperature. So you can observe this diurnal dynamics that diminishes when the drought intensifies and water is getting scarce in the soil.
Only 2 more minutes.
Oh, hurry up. So I will combine it with this gas exchange measurements. So using this WALS GFS 3000, and in the top bottom you can see the spectral engines sensor. And assuming that there's quite a uniform layer of water within the leaf, and the relationship between leaf water content and spectral reflectance is linear, we can get from the transpiration measurements, we can, after cutting the leaf from the tree, we can use the transpiration measurements to calibrate the spectral measurements. We did some test altering PPD light and CO2 concentration, and the results, so we could quite nicely get from a single leaf the relationship between, for instance here, reflectance and 860 nanometers and equivalent water thickness. Very linear relationship there, and the root mean square error was varied between 0.2 to 0.5 grams per square centimeters. So you can quite accurately get to the natural dynamics. Here you can see that when we increased PPD step by step, transpiration on the red and our estimated leaf water content with the black, we can observe that there was quite instant changes in leaf water content that we haven't been able to observe before. Similarly to when we decrease the CO2 step by step, we can see an increase in transpiration, not much of a change in leaf water content until the cutting, but also we are going towards the evening, so the leaf water potential of the tree is decreasing. And then for the light, similar, so we are increasing the light step by step, and we can observe that the results kind of make sense. We have an increase in transpiration and decreasing leaf water content. So it's kind of a new method for easy calibration of reflectance measurements. You could observe quite fast responses to the leaf water content when PPD was changed. For larger leaves, maybe have to consider also the other part that is not within the measurement cuvette, and I think this could really open some new possibilities for looking at different interactions between leaf water content, transpiration, and carbon exchange. And then the question is how to put this in the field. This is super proximal remote sensing to very small level, but how to then get to the bigger picture. Okay, thank you.
Thank you so much. This is very rich information. I enjoy the presentation. Thank you. Unfortunately, we do not have a time for question, so maybe we could revisit this topic at the when I have time at the end of this the meeting. So the next the presenter is the Dr. Fred Humerich. So Dr. Humerich is the founding SpecNet member. And he has extensive experience in extracting information on biophysical variables and land cover types from remotely sensed data using both computer programs and also the field measurements. His research interest includes the use of remote sensing to describe biophysical characteristics of terrestrial ecosystems, and to utilize the information to improve our understanding of ecosystem processes. The title of his talk is Reflectance of Fluorescence in Cornfield.
Thank you, Yuki. Can you see and hear me all right?
Yes.
Okay, great. So today I want to talk about some work that we've done using a tower-based system to relate optical signals with carbon fluxes. So the system we're using we call Fusion, and basically it consists of a temperature-controlled box that we have upward and spectrometers in them, and the spectrometers are paired for upward and downward viewing. So there is, you can see my arrow here, there's a rod pointing up here with upward looking fiber optics, and then within this case are downward looking fiber optics. And we can measure both spectral reflectance and fluorescence using this system. And our tower is placed in the middle of a cornfield, and the Fusion system scans around, making measurements at multiple view and zenith angles. And although today I'm just going to talk about just looking at one direction out of it, not looking at the whole field. And then in the same field with that is a flux tower that measures CO2 and energy fluxes. And so we're going to combine those data. These data were all collected at the USDA Beltsville Agricultural Research Center, not far from Goddard Space Flight Center where we work. So basically, we have timed the way the Fusion collects data to collect data at about half-hour intervals to match the half-hour intervals of the flux data. And I'm going to present data that were collected over 2 growing seasons. And altogether, we have a little over 1,100 half-hourly observations going through the entire growing season here in 2014. So this is showing NDVI in black and PRI in red, the photochemical reflectance index. And basically sort of the width of these points are showing kind of the diurnal variability of these indices. And along with the seasonal pattern you can see of green up and then senescence. And then this is also within this, we're measuring gross ecosystem production from that we got from the flux data, and solar induced fluorescence. Here we're just looking at the fluorescence from the O2A band that we calculate using the 2FLD approach. Again, one of the things you can see in the data, not only you're recapturing whole seasons, but these 2 different years have very different productivities. That the maximum productivity in 2014 was really much higher than the productivity in 2015. And so we're trying to look at, can we develop an algorithm approaches that are using these optical measurements that we can actually get retrieve flux values at half-hourly intervals over these entire seasons, and 2 different seasons that are quite different. So sort of as a baseline for this is just using NDVI. NDVI is our favorite index. It's a classic, and frankly, it doesn't do that bad. If we use NDVI to calculate, use NDVI, a linear function of NDVI to calculate the fraction of absorbed power, and then use the incident part, which we can calculate from the incoming radiance from our sensors, that calculating absorbed power doesn't do a horrible job. I mean, there's a lot of variability here, but it's describing over 60% of the variance in across multiple seasons and at half-hourly intervals. So diurnal and seasonal variability. But can we do better with more information? So this plot is showing the fluorescence versus the PRI for all of these points. And then the color of the points is the productivity. And so you can see this sort of pattern that, you know, at low PRI and low SIF, we have low GEP. But as we get up to higher values of GEP, we find that, you know, PRI can have both low and high values. At high values of PRI, we can have a range of values and SIF too. That PRI and SIF alone really are not explained, cannot really explain all of the variability in GEP, as you can see in this figure. So what I've done is I've really just produced a completely empirical approach to this, and basically divided this space up into two types, just by drawing this line across it. And within this lower area, basically we find that there is a pretty much a solid trend between PRI and SIF with GEP in here. But in this region, they don't really give us the information we need. And in that region, I've just fallen back to the NDVI and PAR relationships that I was showing in the previous slide. And if we do that, it significantly improves the results. That by doing that, we have half-hourly GEP, again, through all of these seasons. And now we're describing 79% of the variance in that, compared to the 63% of just using NDVI and PAR alone. So by bringing in this new information and using it judiciously, we can significantly improve our retrievals of GEP. But we don't have to do this with, we don't have to, but it's not clear, frankly, in this analysis using SIF, and I'm only presenting a couple of approaches here, but SIF was really hard to blend into this and use in ways that were productive. And in fact, just using the spectral reflectance can be just as useful. So here is, I basically used a partially squares regression using 90 spectral bands out of the reflectance data, and training on a random selection of 250 points. And this, not using any SIF data, describes 80% of the variance in the data. So I do just as well using spectral data instead of using fluorescence data. Yes.
1 more minute.
Okay, I'm just about done here. Thank you. The one other point I want to make about this is that it was really important in doing this training to use data that use training data that came from all seasons. If I focused on only a single season, then it really wouldn't work. And finally, just one more point is, because this fusion system does scan this area, we actually can use it to scale up to satellite-sized pixels, but I'm not talking about that here, but just as a mention. So that's it. Thank you.
Thank you, Fred. I have a little time. We have a little time for questions. Is there any questions?
I have a question about your comment, Fred, about the SIF versus reflectance. How much do you think that's sort of an aggregation issue, signal to noise issue? Do you have a sense of, I mean, SIF obviously works well over certain timeframes, but do you have any particular comments on why it wasn't working as well at that scale?
Actually, no, I actually don't have a good sense of why this isn't, why the SIF doesn't work. Because but it was just, I tried a whole bunch of different statistical approaches to blend indices and SIF. And frankly, I really had to work hard to get information, to get these statistical approaches to use. If they had an option to not use SIF, they almost always did, unless I did something to really push that in. And I'm not entirely sure why.
And there's a
So-
comment too, a question from Paul Stoy. I don't know if we have time, Fred. Did you explore NIRV or NIRV in radiance space?
No, I haven't looked at that.
Okay, thank you so much, Fred.
How do I stop sharing my window?
Yuki, Ben also had a question, had a raised hand. I don't know if we have time for one more
Yeah,
question.
we probably wanted to move to next presentation.
You can send your questions directly to the speakers in the chat as well.
There we go. Stop share.
Okay. Hi. So our final speaker before the break is a Dr. Lars Eklund. So Dr. Eklund is another founding SpecNet member. His main research interest is the use of data from satellites from collecting land surface information, primarily concerning vegetation. The title of his presentation today is a site spectral and providing multispectral data for ecosystem monitoring.
Thank you for the introduction, and it's nice to be here. So I will not give a very scientific speech, mainly talk about what we are working on in Sweden that is related to SpecNet. So I'd like also to mention my co-workers, Virginia Garcia, Shanghai Shatapa, Hong Chao Jin, Carola Olson, who have been doing the real work behind all of this. Right. So the kind of measurements I'm talking about here are mainly multispectral and power measurements using relatively simple and robust instruments. So we do operate also other kinds of hyperspectral sensors and so on, but for long-term measurements, we find that these simple sensors are quite useful. So measurements in various points above and below the canopy at different sites. So we started several years ago to develop measurements across the Nordic countries to collect spectral data. We call this NordSpec. And it was very much inspired by all the ideas of John Gammon and what came out of SpecNet. And the idea was, of course, to add satellite data validation capability and also to be able to improve on process knowledge using the measurements. We also gained a lot from some European collaboration projects that were ongoing in those years. The Eurospec project, later on Optimize, and today the Senseco project is still running. And we opened up measurements across several different ecosystems, and you can see that we tried to cover latitudes from very far north until pretty far south, actually, even down to Africa. And this was useful, and we learned very much. But I found over the years that it was very difficult to maintain all these sensors and instruments. And I didn't have really the manpower nor the financial power to continue much of this. But many of these are still running. But anyway, what came out of these measurements and what is still very much in the center of our work are maybe two different streams. So one is the improved process understanding, working on GPP, phenological stages, and understanding the different time signals. You don't have to pay so much attention to the graph. It's mainly to show that by using these multiple measurements across time and across the phenological process, we can learn quite a lot. And one of the most significant things that came out of this work was the development of a new vegetation index. We call it the PPI, the Plant Phenology Index. And it's an index that is linear with green leaf area index. And it has the good capability of being insensitive to snow background variations, which is very difficult when you want to work in Nordic countries where we have intermittent snow, and disturbing the satellite observations. Another thing we have been working on is to improve our methodology for time series processing of satellite signals. We have used these data from the ground sensors to compare and to calibrate our different data smoothing algorithms. And this has also been very useful when we developed the new processing methodology that we use in the new time software package. And we have now developed a method that works well with Landsat and Sentinel-2 time series data. Right, so something else that came out of these measurements over the years was the importance to do good sensor calibration. So some of the co-workers in that time and members of the SpecNet community showed us that there was really quite a drift in many of these sensors. And I think it's very important to stress that if we don't calibrate our sensors, that they are not very useful for multi-year measurements. So we developed an in-situ sensor calibration that we felt was very useful because we didn't have to send the sensors to the UK, for example, for calibration, but we could do the calibration at the site. And we published a paper on that in 2015. And it's quite useful because it's actually as accurate or even more accurate than the manufacturer calibration methods that many people use. So, but finally, I found a home for our measurement, and that is the SITES, the Swedish Infrastructure for Ecosystem Science. SITES is kind of a, let's say, a miniature NEON project where we have ecosystem stations across Sweden covering different ecosystems. I've listed mountain heath, wetlands, lakes, forests, agriculture. And within this network, we have opened up the site spectral project. This project has now funding for several years. So that means that we have been able to set up sort of a very good infrastructure for conducting these measurements in a much more professional way. So what we do is we carry out year-round multispectral measurements. We do seasonal drone flights. We have phenology cameras, and we also collect satellite imagery to be able to portray these ecosystems. We have staffing and financial stability, which enables long-term data collection and quality control. So we've also developed a series of data products out of these. So we have phenocams, multispectral sensors, UAV, satellites, and we present data going from the raw data up to different levels of processing. We use defined data collection protocols. We have metadata. We also provide quality flags and documentation for all the data that we present. So the idea of this is to be able to make the data useful, not only for ourselves, but also for other researchers. So we can think about different target groups here, and I mentioned that, let's say, biogeoscience or the carbon and water flux community, who are interested in very specialized measurements, and where I think that some of these reflectance data can be quite useful, and I know from personal experience that they are very useful. We also have the agricultural and forest community that will be interested in using many of these data. We have the remote sensing community. We have also a wider field biology and ecology community that I want to reach out to, because this is actually the bulk of people visiting these ecosystem stations. And it would be very nice to be able to collaborate more with them. And of course, these data are also very useful for general outreach. So we not only need the very specialized, let's say, time series data, but we also need some other more general data products. So phenocam data
2 more minutes.
Thank you. Phenocam data are useful because they are visual, but they also provide some time series that can sort of portray the data. And here we see evolution through a clear cut. We can see how green signals increase with the growth of the vegetation, or the regrowth of the vegetation. We also collect the UAV data, we present orthophotos, multispectral data, and we generate some digital terrain models. We've also been working on some calibration methods and methods for best practice for deriving temperature data, and also for radiometric correction of the multispectral data. So all of these data are open and freely accessible. So I would like to invite you to visit Sites data portal. You can see the web link down there, data.fieldsites.se, and check out the data. We haven't really finished all the documentation yet. We are at the final stages, and we are also hectically uploading data to fill up this data site. And that's it. Thank you.
Thank you so much. Any questions?
Lars, this is really impressive to see that you have this long-term study. Do you feel that you've solved some of these technical problems, or are you still bedeviled by technical problems and have to replace things constantly over a network like that?
Yeah, that's a very good question and comment. That's basically why we try to do things as simple as possible to minimize the risk of problems. And of course, we can get criticized that the instruments are pretty simplistic sometimes, but I think getting some kind of long-term stability is maybe the most important for us at this stage. So we are fighting problems, but it's there all the time, I think. The good thing about sort of attaching to an existing infrastructure is that they have field staff and technicians out there who can work on these installations all the time. So that really helps, I think.
Thanks very much.
Thank you. So let's take a 11 minutes break, and let's come back for the part 2 and the 35 after, wherever your time zone is. So if those who wanted to stay and asking questions with the chat, I believe we can do that. Is that correct, Giovaldo?
Yes, absolutely.
Okay.
The session will stay open here, and while we are on a break, I'll take the chance to remind folks to take a look at the poll again, and let me just share my screen quickly here to show how that looks like. We have some results coming in. Just a quick question on where folks are from. We kind of have a good coverage, spatial coverage here of the globe. Quite a few folks from Europe and across North America. We can revisit that later, but this is the interface that you see when voting. So you get the first question, that is that one that shows your location. But if you head here to the Q&A, you have an opportunity to add your suggestion to breakout sessions and vote as well on which one of these you think would be a good breakout session. So please do that throughout the meeting. If you see a good question coming up during the talks or anything like that, feel free to suggest a session here. And we'll use these to create the breakout rooms at the end of the meeting. And if anyone has any questions, any trouble finding information, I just see Dave asked about schedule, and Trevor posted that. Thank you, Trevor. And if anything else comes up, please let us know. Otherwise, we'll be back in about 9 minutes.
Hello, Gilbert. So can I still ask a question? Oh, no.
Yes, go ahead. Let's see. I think Lars might still be online.
Right, yeah. Yes.
Okay. Yeah,
Great.
I think I just missed a chance to ask before. So first of all, I think it's really nice coordination about all the measurements for the spectral measurements. So I was wondering, because before I also read a paper of your paper regarding the PPI index. So I was wondering, have you ever explored that using, so because for example, in early spring, that might be with slow melting, that the FA power will be overestimated. So I don't know if you have explored this with PPI, it can be improved these aspects.
Yes, we have in fact looked at how the different indices behave during snow melt, and the PPI is very stable during that transition period. So whereas, for example, the NDVI jumps up from very low value to very high in exactly simultaneously with the snow melt, the PPI stays more or less constant during that period and slowly, gradually grows during the sort of development of the leaf canopy.
Okay.
So that was one of the reasons why we developed the index. And I think there is if you look at the 2014 paper, there is a graph showing that process.
Yeah, because I'm working on some modeling using the just not use vision model. So if I just using the NDVI or some conventional index, basically, it's hard to kind of capture this FFR, real FFR changes during the early spring. But if I can solve it, I think it definitely will improve somehow. Yeah. Last question about the phenocam and the spectral measurements. So how long these measurements covered, basically? Because probably I'm quite interested to use your products or your data or some kind of.
We have some instruments have been operating maybe 10 years or something like that. We haven't published those long time series because we need to go back and apply the calibration coefficients and so on. But for some single sites, we have pretty long time series, but not for all the sites.
Okay. You mean for the mute spectral measurements or only for phenocam? Both?
Oh, for the phenocams, we have some pretty long time series, maybe 10, 15 years. For the spectral data, it varies from maybe 5.
Okay.
Between 5 and 10 years.
Okay. Thanks a lot. Quite looking forward.
Hi, well, welcome back. It's 35 after the hour, whatever hour you're in. I hope everyone had a quick chance to get some coffee or something during the break, but we're going to start this second session with one of the long talks from Taylor Jones, who's at Boston University. And Taylor designs and builds various environmental sensors, including wireless sap flow in trees and remote sensing of solar-induced fluorescence. And he's going to talk about a sensor for making remote SIF measurements in complex urban landscapes, initial findings and plans for collaboration. So if you're ready, Taylor, please take it away.
Okay, can everybody see me, hear me, see my slides?
Yes, you're good.
Okay, great. Yeah, so thanks everybody. And I want to say thanks for getting invited to give a talk here. This is a group that I don't have much experience with, but I know does a lot of stuff that I'm really interested in and that I'm kind of new to. So I'm really excited to get feedback from some of the experts in this room. So I'm going to be talking about work that I've been doing at Boston University with some of my colleagues here in Lucy Atira's group and with some colleagues at NIST in Gaithersburg, Maryland. And we're talking about SIF, and we're talking about SIF specifically in urban landscapes, which are historically pretty tough to measure in. So wanted to start by talking about the satellite scale, which is kind of our motivation for trying to get good SIF measurements to calibrate what's going on with the satellites. So this is an example target from the OCO3 SIF sensor. And you can see a couple things. We have, OCO3 has great high spatial resolution because it does these target maps. But there's a lot of noise, and since it only kind of snapshots us every couple weeks or so, we don't get really good diurnal trends or a lot of the other kind of data that we'd want. If we look at kind of the last couple of years of OCO3 data from Boston, this is for targets in Boston and hour and a half away at Harvard Forest. You can see a couple things. One, you do get a reasonable seasonal trend. It's lower in January than it is in July. But other than that, there's a lot of spread here in these box plots. So again, a lot of noise in sort of each target. If you look specifically at, this is a correlation plot of 2 days in June of this year from two OCO targets. You can see the sort of the median value is about the same, somewhere 1 to 1.5. But the correlation pixel to pixel is not great. And there's a lot of reasons for that. And so we kind of wanted to see, okay, well, how can we design a sensor to help understand these satellite measurements, validate, characterize whatever we can do from where we are in Boston. And so when we started thinking about that, we looked at, well, what is this satellite seeing? So this is a single pixel from the OCO3 target that I showed earlier. This is the one over Boston. You can see the red dot is Boston University. This area of open space here is Fenway Park. And not too surprisingly, you see that 60% of this area is impervious surface, but there's also a lot of other stuff going on too. There's a fair amount of what's classified in this inventory as forest, but is sort of street trees and planned trees, and then a fair amount of open space. And if you look at the view from our roof here at BU, kind of over the campus quad, you see all those same things. You see a lot of grass, a lot of trees, a lot of buildings, the Charles River, and this kind of breaks it down into how much of our field of view each of those sort of circles that I drew here takes up. And so we really wanted to design a SIF instrument that was made to not only look at the big picture here, kind of that big red circle, but try to figure out the different constituent target types that we'd be looking at. And so after a couple iterations, this is what we ended up on. So this is Cameron. He's named Cameron because he's attached to a camera. And the basic principle of Cameron is based on the photospec design, which probably a lot of you are familiar with. So we use the same QE Pro spectrometers that they use. So we're able to get SIF, PRI, NDVI, EVI, various other indices. The big kind of differences here is that we've aligned it with this, high resolution security camera. So we get RGB images, kind of like a phenocam. This one in the picture here also has a thermal channel. Just wanted to give a shout out to Miriam for a very cool talk. And I have lots of questions about how to deal with thermal data. So I will be sending you an email later. We also added a larger telescope to let more light in. And then the other big difference is that this version has a variable field of view. So there's an iris inside that's programmatically controlled with everything else. So we can go to different targets, change the size of the field of view we're looking at, and then try to look at that data and see how those things interact. So we've built a couple of these instruments, both on the roof here at BU, we've one at Harvard Forest, and also one that's at our test site at NIST, again in Gaithersburg, Maryland. This is just kind of just a little layout of the optics here. Again, it's just strapped to the top of the camera, carefully aligned, of course, and has a field of view that goes from about 1 degree to 15 degrees, both of which fit well within the camera's field of view of 35 degrees. And then to get downwelling measurements, we simply have the camera look upward, and then there's a little shelf that has a diffuser there, so that we could get kind of the downwelling irradiance from that. Big themes so far today, calibration. So the alignment and calibration are as critical for us as they are for everyone else's instruments. So alignment and field of view calibration is done by backlighting the fiber, so the fiber coupled halogen lamp. So we just shine that out at nighttime. Here I'm targeting my lab mate Ian Smith. So holding a piece of paper about 100 meters away, and using that we can kind of dial in the alignment, and that also helps us characterize the field of view from the iris. Radiometric calibration, we're using NIST traceable integrating spheres. The collaboration with NIST for this project has been very valuable. They are certainly experts in all of these subtleties involved with calibrating these kind of radiometric sensors. And we're continuing to try to beat down the errors in that and do the best we can with their help. Okay, so what does this data look like? So here is just one day of kind of clear sky summer data from Cameron. So here I have the full view shown in the red. SIF values here, middle of the day, a little bit below 1. This is consistent with the OCO3 values for deep in the city, so nothing too surprising there. The tree target here is higher than the full view target, which makes sense. There's more SIF per area in the tree target. But what's really interesting is kind of the relative values of these and seeing how they change throughout the season, throughout the day, and also in different conditions. So the grass target down here, you can see in the afternoon is higher than the tree target, but in the morning is lower, and that's because in the morning it's shaded. So in this image here, you can see that there's that brown circle is shaded. Obviously, shading is a big part of driving these SIF signals, and in urban areas, shade's really important because you have tall buildings and you have trees that kind of stand out by themselves, and so it really helps to understand what's going on there. And then we also do non-fluorescing targets. So we look at the roof of this building and we look at the Charles River. And what you see there is SIF retrievals are low, but they're not zero. And this is probably an artifact of how we're processing the data. We're using the PhotoSpec DOAS retrieval, a version of that. But it's certainly important for us to understand how these other targets are affecting the numbers that we're retrieving. So I mentioned before that shade and composition are really important in this. And luckily, we're snapping images with this camera every time we take a measurement. And that allows us to do a lot of really cool stuff, including analyzing the field of view. So here's that same day of SIF measurement targets. And you can see that we've broken down this image into different types. And then we have a little kind of method for determining what pixels are shaded and what pixels are not. You can see it does a pretty good job here, and you can see how the shade kind of rolls across the quad there in the middle of the day. And if we look at how that looks over the course of a day, here's fraction of target for both the full view and the grass target. And you can see just how important these things are, especially in the grass target. And you can see how good a job our shade detection does at determining that as one of the things that's affecting our SIF measurements. So we're pretty excited about kind of this initial look at our data. We now have months of data with this type of system that we're now using to really study the relationship between SIF, land cover, and lighting conditions. So that's not just shade, but that's also cloud cover, which again, we're taking sky images. So we have a good sense of cloud conditions throughout the day. And now we're really trying to understand how these things relate to each other. And we're not just using Cameron, and other people have mentioned how important other types of measurements are. So we are measuring other vegetation indices, but we're also measuring a lot of stuff on the ground. So this is Julia Mars and our group here with a Y core measuring leaf level gas exchange. We're also doing sap flow measurements. We're doing punches to look at pigment content. To really try to understand energy partitioning in these urban trees, throughout the day, throughout the season, and really trying to understand SIF's role in this whole energy partitioning problem. And she's got a lot of really interesting results, and she's shown seasonal trends in the energy partitioning, seasonal trends in chlorophyll content. You can see here how later on in the season, the sort of PRI-SIF relationship changes as the leaf is doing different partitioning there. And again, also with the sap flow measurements. And having these images has done a lot for us in ways we kind of didn't expect. So for instance, this is a whole season of the SIF versus PRI data. And we've actually been able to explain some of the outliers using the Cameron data, so using the image data. So for instance, this was during a high wind event. We had data that really didn't fit the normal trend. We went through and looked at some of the images and found that the wind was so high, it was actually flipping the leaves over, and we were getting a lot of underside of the leaf. Which we wouldn't have known had we not been taking these kind of pictures. So that really gives us the ability to understand different events. We've also had things like they set up a tent in the middle of campus for whatever reason, and we're able to see that and filter that out of our data. So we're still discovering new uses for this instrument. And as I mentioned before, we do have a couple other deployments. So at NIST in Gaithersburg, which is studying a site that we've been making a bunch of measurements, sap flow, lots of respiration measurements throughout this 100 meter by 100 meter plot. for the past 3 or 4 years now, and monitoring SIF from the roof of that building. And then also in Harvard Forest, we've been taking measurements from up on the walk-up tower there. And also in addition to this, I believe Troy Magney's latest instrument is sort of based on this design too. So it's definitely getting some traction out there, and the data is starting to pull in. And so now that we have all of this SIF data, we've discovered that we really need to understand how to process the data and how to calibrate these systems well. And Julia Mars and our group had a paper that came out this year that was a review of SIF data in the literature and showing how there's sort of orders of magnitude of different values reported, and how there's not a lot of consistency in how these instruments are built, how they're operated, how they're calibrated, how they're processed. I think I'm definitely speaking to the choir here. I mean, I think that's kind of one of SpecNet's big MOs, is that they're trying to bring these people together and try to iron out some of these difficulties. But the exciting thing about our collaboration with NIST is that they've shown an interest in really kind of taking charge of an effort to solve some of these problems and starting to standardize some of these processes. And actually, Julia Mars, who's about to graduate, is going to start a postdoc at NIST in the spring to start tackling some of these issues. And so when we started talking with them about these issues we were having, and sort of started brainstorming some intercomparison project. Similar things have happened in the past, but we thought we were in a good position to try to lead one of these. And so we started coming up with ideas about things we could do to be part of some sort of sensor intercomparison cross-calibration event. And we ended up writing a survey that some of you probably saw. I know some of you saw. We floated it around as best as we could, and try to get a sense of how much desire there was in the community for some sort of cross-calibration event. So we had a questionnaire that was 6 questions. We got 25 people to respond, including a lot of people that are actively making SIF measurements. And 16 people responded saying they'd be willing to participate and actually sacrifice some of their data collection time to bring instruments to this. So we thought that was a really strong positive response. And people were willing to give weeks of the growing season up for an effort like this. And we also asked, how important are these different things that could be part of it? You can see there's not a lot of not important or no opinion on here. It's a lot of very important or somewhat important. And people seemed most enthusiastic about getting sensors on towers in the woods, making measurements alongside other people, in addition to doing lab calibrations and measuring with satellites or other things like that. So people really want to get them out in the field, do apples to apples comparisons, which we totally agree. We also asked about activities surrounding SIF data, and I know there's similar efforts sort of in various stages of discussion and implementation about centralized SIF data repositories, open source retrievals, and workshops. Great, and we're not trying to duplicate efforts that are already underway here, but certainly we want to line our efforts in line with whatever else is going on in the community. So I'm really interested in getting people's feedback on all of this. So sort of in summary, I talked for a while about Cameron, which is our new instrument, and the kind of initial measurements we've been making in Boston. talked a little bit about some of the other measurements that we're making and how those are getting kind of folded in. And then I talked a little bit about our efforts leading an intercomparison at NIST. And that, that project is still in the planning stages. We'll probably know a little bit more about timeline and scope once the federal budget kicks in, whenever that is. But we've got a couple funding sources that we're exploring with that, and a lot of interest from NIST. So, at this stage, please reach out if you'd like to be involved in any way in that, or just have any kind of feedback in general. And my email is here, and of course, this is my son, my lab assistant here on the right, who helped me assemble this particular camera. So thanks everybody for the time, and I look forward to any questions.
Thank you. Are there any questions? I'll ask some questions. So there's a strong bidirectional effect to SIF emissions, and so in trying to intercompare different sites and also scaling to satellite data, how do you have any thoughts on how we deal with that?
I don't. I know that there certainly are, and there's certainly a lot of people that are trying to figure that out. I don't have a solution for it. It's certainly in the list of things that I need to try to deal with. I think there's a lot of issues scaling to the satellite scale, especially in complex areas like this. And I don't have any false hope that I think we're going to be able to nail, pixel to pixel variation. But we want to see kind of how good we can get, and try to understand and quantify what we don't know, is kind of where we're trying to go. But yeah, I don't have an issue I don't have a solution for the viewing geometry problem, other than I know it's there, and I'm looking for a way to solve it.
I don't see another question, so I'll just keep asking you questions.
I have a question
too, actually.
Okay, please.
Thanks for a great talk, Taylor. I'm glad that you're leading some efforts and kind of gathering information about interest in instrument intercomparisons for SIF. One thing I'm curious about, though, have you thought about trying to include measurements of some kind of standard, instead of just measuring, say we all measure vegetation with different instruments? This is something I've been thinking about because, it's possible that all your instruments maybe they all agree, but they're all wrong. I'm kind of curious what your thoughts are on that. And certainly, with NIST, they're good partners to think about that type of question.
Yeah, they love standards. It's in the name. Yeah, no, definitely. I think that in our discussions with them about how we would set up something like this, we'd have various vegetative targets ranging from tree canopy to probably closely manicured grass targets, but also various types of passive and active targets for that purpose, to try to bring it back to some absolute numbers, because you're definitely right. They're sort of two different problems, getting the relative and the absolute there. But I think NIST would be a good spot where we could tackle both.
Okay.
I have a question. If I caught it correctly, your PRI-SIF relationship was the opposite of Fred's. I don't know if I got that correctly. Do you have any comments on that? The direction, I mean, it can be different, and it can be the opposite, depending on circumstances. I mean, you see dynamics here, but
is that opposite? I know his axes were switched.
Okay.
So I can't remember what his looked like.
Yeah, I think it's actually the same, because the axes are reversed.
Okay, thanks.
Scared me there.
No, we're all good.
Now, this can happen. It depends on the context a little bit. So I just thought this might be an interesting comparison, but maybe I'm remembering correctly here.
Okay, well, thank you. Let's move on. We need to move on. Our next speaker is Trevor Keenan, and who is at UC, assistant professor at UC Berkeley, and he's going to talk about a project to support international collaboration, network synthesis, which is something that we in SpecNet are very interested in. So, Trevor, please take it away.
Hey, everybody. Can you hear me and see the screen all right?
Yes, it's good.
Super, cool. Yeah, I'm also very excited to be here and talk about ways that we can foster collaboration between the SpecNet and Flux communities in general. And it's great to see in the breakout suggestions that that's one that's rising to the top in terms of votes and popularities, trying to figure out ways we can do that better. And so I'm excited to talk about the FluxNet Coordination Project, which is a recently funded initiative it's pretty much focused on that, building collaborations. So we have a lot of resources and opportunities to think about in terms of how SpecNet community researchers could more deeply engage with Flux community researchers. Just to present here, I'm going to talk briefly, and hopefully we'll try to keep it to time, about the FluxNet Coordination Project. And so this is a project recently funded by NSF to help coordinate FluxNet. So let's see if I can. So I'm sure you're all pretty familiar with FluxNet, and just to say that it has had a long history, and it's grown over time, and that has been really aided by researchers in the community primarily. It's pretty much a grassroots-driven initiative, contributions from researchers all over the world to build a large Flux network, and something similar to what SpecNet is doing. But of course, it has been running for longer, so it has grown to be bigger. It has had various different sources of support over the years. So we had NASA and DOE support initially to get the network started, and then other sources of support from Research Coordination Network, support from NSF. That actual funding culminated in the SpecNet FluxNet meeting that we had in Berkeley in 2011, which was a really awesome meeting. And then the more recent generation has been some DOE support from the data perspective, but really it's been many years since we've had formal support for FluxNet. So I'm excited to announce the FluxNet Co-op, which is funded through NSF's ExcelNet program. ExcelNet is focused on accelerating international network of networks collaborations. And so they've provided $2 million for us to help build the next generation of FluxNet and to broaden the communities involved in FluxNet. And so that also means, of course, SpecNet and lots of opportunities for SpecNet engagement. So, oh yeah, I meant to say at the start, I'm actually not going to talk today about spectral measurements at all, even though in my group, we just started field testing a head-wall SIF imager, and we're really excited about the different science questions we can do with that and how we can collaborate with all of you in it, but I'm not going to talk about it today. What I'm going to talk about is how this FluxNet Co-op, as we're calling it, is structured and what kind of opportunities it provides. So it is a collaboration of all the multiple regional networks around the world, of which there are many, and they're all coming together to form a new FluxNet Community Council. And this council will be the governing body of the FluxNet Co-op and help guide the initiatives for FluxNet for the next 5 or 6 years as we help build the next generation of FluxNet. And so we have various different initiatives designed under this project. So those are focused around education, data development, and community building. For education, we have something we're calling secondments, which are prolonged stays by scientists in host institutions. So say you have a strong you want to build a strong collaboration with scientists in a foreign country, we will fund you to go there, spend a period of time, could be 2 weeks, could be a month, could be a bit longer, to build collaborations and do focused research on a specific topic that would benefit from you being deeply engaged in that host institute or host group. So these are, we have quite a few of these, primarily focused on early career scientists. So early career support is a real focus of this FluxNet Co-op project in general, but also for people at other career stages. So we have regional experience exchanges, which are similar, but thinking about getting people together to talk about specific questions that are common across regions. So say you have, you're studying an ecosystem with specific characteristics, and there are other such systems around the world where scientists are approaching the problem in different ways with different instrumentation, and bringing those people together to really hash out how we can learn from each other and what novel questions we can identify. We have a strong collaboration with FluxCourse, which I'll talk about in a bit. And we have lots of diversity and inclusion initiatives to really foster a diverse next generation of scientists involved in flux research, and multiple different strategies for doing that. On the data side, obviously super important, right? FluxNet is in part a data repository, and it, as you know, the last release was FluxNet 2015, which is quite a while ago. We'll be coming up in not too long on the 10-year anniversary of that. And so we're really focused on moving the database towards the next generation of a more open, community contributable framework where we are less dependent on this one big release every 10 years or so, and having a more dynamic database that individual networks can directly contribute to. So we're going to be putting a lot of effort into this, developing code pipelines, processing options that are perhaps regionalized for specific ecosystem type idiosyncrasies, open FluxNet processing code base, standards for all data and metadata, and also thinking about novel data types. So far, we've been thinking about methane, and there's been a lot of work on that. N2O is a growing measurement in the community that people are making. Spectral measurements are another type of measurement that we could think about. We're going to develop APIs so to allow easy access to data, programmatic access, and also developing added value products from the database. So really building the utility of the database for the community. And one of the key components is the third, community building. We really want to build a community. And it's interesting to think about how to do that in the modern times where COVID dictates a lot of the nature of our community interaction, unfortunately. We have, this proposal was written primarily in pre-COVID and thinking about a world in which in-person interactions were the norm and the standard for interactions. So we had planned 3 project conferences, one hosted in Europe, one hosted in Australia, and the third hosted in the US, likely in Berkeley. Lots of side meetings at established conferences, special sessions at AGU and EGU, for example. Regional exchange workshops, where we have funding for a few workshops every year to bring people together to discuss specific topics. And these will be workshops proposed by the community. So we're not selecting priorities. We're going to ask the community, 2 minutes, which Trevor. Includes, 2 minutes?
2 minutes.
Okay, I think I'm at 8. Okay, I'll speed it up. So when I say the community, that means you, that includes you, right? FluxNet is a community of data users and providers, and all people thinking about Flux and ecosystem function. So when we are looking for workshop suggestions, that includes you. You can submit those suggestions. Okay, so I'm going to move along. I will largely skip through this, but just to give you a sense of the community council, what it looks like. So we have a chair, co-chaired, who's yet to be determined. We haven't really even started this project. It officially starts in January 1. So we're still building this out. We have an education and outreach lead, the network coordination leads who bring in that historical perspective, regional network representations, early career representations, and Neon as data integration. And subcommittees, of course, we can't do any without committees, so we will have lots of them, and these are opportunities for you all to get involved. They'll be broadly advertised. We'll be looking for volunteers from the community to step up and get involved in moving this all forward. So because of only 2 minutes, I'm going to skip through FluxCourse just to say that FluxCourse exists. It is a very useful resource for the community, something that is really good to send your students and even postdocs to. We do have a lot of modules on spectral measurements, particularly as well. And so it's something not just for eddy covariance community, but also for the SpecNet community, even though there's a lot of overlap too between those. But yeah, just to put that on your radar, we have funds to support students to go to FluxCourse. And FluxCourse, we're actually trying to make it free for everybody next year. It wasn't held last year or the year before. Next year it will be. And so just to put that on your radar. Skip this as well. So how does this all fit together? So it is US funded, so primarily the funds are for US participants, right? But you can be a host institute to US participants going to your non-US institute. We also have funds for international host people to come to the US to stay at a US host institute. We have funds to bring people not from the US and in the US, all folks to 2 domestic workshops per year, and opportunities to support 3 international scientists per year to come to the US. And we will be, and also for our project meetings. So we will have calls for these events. We will be asking you to submit proposals for these exchange opportunities, and so look out for those. So how do you look out for those? Join the mailing list for FluxNet, and follow us on Twitter at FluxNet Co-op, or the Early Career Scientist Network, FluxNet ECN, and that's where we'll be announcing a lot of these opportunities. Okay, thank you for your time. Sorry I went over a little bit. Do follow us on Twitter to get updates or join our mailing lists. And yeah, thanks. Happy to take any questions.
Great, thank you. I think we have time for like one question. So from Ben Poulter, what are plans for underrepresented groups and institutions to become engaged? Any training career pipeline concepts in development?
Sure, so FluxCourse is one of the major ways in which we will do that. So this is training, essentially a training program, and the funds will be prioritized for underrepresented group applicants. We'll also have a lot of training materials built into that from the perspective of implicit bias training for the instructors and also people involved in any of the activities in the network. Obviously, underrepresented group involvement is really tricky to do. Often we find that we just don't have representation in the pool of applicants. So building out that applicant pool itself will be one of the challenges that we're going to tackle.
Thank you. Okay, we need to move on to the next speaker. Our next speaker is Ben Poulter. Ben is a research scientist at Goddard Space Flight Center, and he's also one of the leads for the NASA SBG program. And he's going to be talking about modeling efforts, coupling the ProSail radio transfer model with the LPJ dynamic global vegetation model to look at reflectance spectra. So this is kind of at a different scale, but a modeling exercise of interest to us. Go ahead, Ben. I'm not hearing you.
All right. Okay. There we go.
Okay.
Okay. All right. Thanks for the introduction. And yeah, it's good to be here. Again, sort of learning about SpecNet and engaging on the modeling side. So I just have sort of a brief presentation. And I just want to talk about some very early work that we're doing. Trying to simulate surface reflectance spectra at global scales using the dynamic global vegetation modeling approach, a specific class of land surface models. And I guess, you know, dynamic global vegetation models, DGVMs, were developed initially to look at the coupled response between dynamic vegetation and the carbon and the water cycle. And so they're very much developed to explore questions related to the carbon cycle at global scales and over long time scales. And I think more recently, there's been interest in advancing these models, particularly because of the new generation of remote sensing data that are coming online. So for example, SIF, which has been mentioned a few times, but also some of the new imaging spectroscopy global missions that are coming online, as well as things like LiDAR waveform and so on. And so the current generation of DGVM models that we work with have really been sort of developed and parameterized for, you know, what we could describe as first generation remote sensing data sets that are mainly sort of multispectral optical missions. And so here we're looking and exploring ways to advance the LBJ DGVM. So so part of the motivation for this is embedded in NASA's 2017 Decadal Survey, which prioritizes observations that inform carbon cycle research. So MI is the most important, E is for ecosystems, and so there's two decadal questions related to ecosystem structure and the carbon cycle that are in this most important category. And so this provides the basis for how we're developing the next generation of missions. So you may have heard of the designated observables, which consists of 4 missions that will launch at the end of the 2020s, with surface biology and geology being one of those. And that is the imaging spectroscopy mission. And so for this set of slides, I'm sort of focusing on GPP. There's a nice paper by Norton et al. In Biogeosciences comparing data assimilation approach using SIF with the data-driven approaches coming from data like what Trevor described in FluxNet, and comparing those with the process models. And they find that the range of global GPP is anywhere from 100 to almost 170 petagrams of carbon per year, which is quite shocking. I think, given that range of uncertainty hasn't grown any smaller over the past 2 decades. And so we sort of focus on GPP and try to understand sort of how this new generation of missions can help us reduce this uncertainty, or better understand the partitioning of this uncertainty to parameters, sort of the theory behind processes, or even some of the drivers. So, as I mentioned, so sort of currently GPP is estimated using mostly multispectral retrievals, and these rely on things like NDVI, which is then used to derive FPAR and APAR. So the figure from one of John Gammon's papers here sort of shows the absorption features that are used to estimate NDVI in the context of the full spectra. And you can see, and we all know that there's a lot more information that could be used to help us make these estimates related to photosynthesis. And SBG, I presented on last time, but it will be an imaging spectroscopy mission providing global 16-day revisit at 30-meter resolution for the full visible to shortwave infrared components of the spectrum at 10 nanometers resolution. And so there'll also be, so this is sort of what we're referring to very generically as SBG Light. And then there'll also be a HEAT spacecraft, which will host a thermal imager measuring roughly 4 to 12 microns in about 5 to 8 bands. And so this will be used both for high temperature features, but also to provide information for estimating evapotranspiration. And we're currently for SPG in what we call pre-phase A, and this is sort of the phase where we go about setting the measurement requirements, and also explore sort of upscoping or descoping components and how that affects the cost of the mission. And at the most recent community webinar, Carrie Nicholson presented some interesting analyses that we've done using intrinsic dimensionality to understand how the information content changes with trades related to spatial, spectral, temporal resolution. And here we are developing a different type of workflow to understand those trades and the mission architecture based around a DGVM, where you sort of start here in this green box where we have just fixed parameters that are related to things like BC max, specific leaf area, and so on. And the DGVMs currently sort of use these fixed parameters as a lookup table as the basis for estimating photosynthesis. And we've simply done a coupling between ProSail and the dozen or so parameters that are needed so that we can generate spectra during runtime of the simulation. And then we run those spectra through sort of a mission architecture where we run the spectra through forward models to get the top of atmosphere radiances, taking into account water vapor, aerosol optical depth, and so on. And then we have an instrument model that then samples the spectra, and then we put those sensor radiances through some sort of atmospheric conversion to come back to the sort of the simulated spectra that the mission would be retrieving. And then we can take those simulated spectra and either compare them to the original and look at the errors and try to understand those, or feed them into PLSR models to estimate back the GPP related parameters and re-estimate GPP and compare sort of the level 4 type uncertainties. So just a couple more slides. This is a table of what goes into ProSail. So we're using Prospect 5B and ForeSail here. LPJ has a fairly explicit representation of the Farquhar biochemical model. And this is coupled to a somewhat unique stomatoconductance model. It's given that it's not ball-berry. And then SLAI is also prognostic and linked back to previous year's biomass and specifically area and grown degree days. And so we've sort of, it's quite difficult to make a one-to-one match between what is needed in ProSail and what LPJ is providing. So we've made sort of various first order attempts at filling this out. And so we're making test runs over the University of Wisconsin Arboretum, where Phil Townsend has a nice time series of spectra that we can eventually compare our simulations to. And this is just some of the sort of diagnostics of what LPJ is producing and that we're sort of linking to ProSail. So here's the seasonal cycle for VC max for the 5 plant functional types, seasonal cycle for LAI, and then soil moisture, which we're using as a proxy for the leaf water content. And so this is what things look like so far. So this is monthly spectra for that location, and you can see that we're currently able to reproduce sort of a seasonal cycle that makes sense, that corresponds both to the LAI dynamics, the influence of VC max, where LPJ uses optimality theory to sort of simulate the allocation of leaf nitrogen throughout the growing season, and then how the influence of soil moisture as a proxy for leaf water content affects the reflectance in the shortwave infrared. This is definitely a work in progress. We're working on integrating snow, branch, and soil reflectance spectra. We have a global daily simulation running now, which is sort of exciting to sort of see how we can, well, see if that works, and to also look at what sort of graphics we can do to illustrate that simulation. We're very keen to compare with field observations, and so we have Phil's data, and then been in touch with Fred and Petya about the Beltsville site. But if you have time series that you'd like to include in this in a model comparison, please get in touch. And then eventually we sort of link this all up with the observing system simulation experiment workflow and feed it into some of the architecture decisions that are being made. And that's my last slide.
Okay, thanks. Let's just do one question. John Gammon asks, can you say a bit more about the scaling challenges when dealing with plant traits or metrics like VC max?
So VC, yeah. So in LPJ, it's a big leaf model, and VC max is the photosynthesis subroutine is sort of parameterized to take place at the leaf level, and then the GPP at the leaf level is scaled to represent what's happening at the grid cell level. I would say it's not done in a very sophisticated way, so we don't have sort of a multi-layer canopy to deal with LPJ, for example. But sort of the way that one interprets how LPJ is set up is that you do go from leaf to canopy to the grid cell with the mixing of the different PFTs.
Thanks. I'm afraid we're going to have to move on. So if anyone has any more questions for Ben, just put them in the chat. So our next speaker isn't actually here. It's a recording. But Troy Magney is distracted right now by his new child. So he's recorded his talk. Troy's at UC Davis, and he's one of the SpecNet board members. And his presentation is going to be on considerations for linking optical measurements to ecosystem carbon fluxes. So please start the recording.
All right, hello SpecNetters. Sorry I can't be there with you today, but hope you all are having a great time. Today I'm going to talk about considerations for linking optical measurements to ecosystem carbon fluxes. I'm going to go through sort of a smattering of considerations and different studies led by a lot of the contributors listed below on some of our collaborative projects. So let's get started. So the outline, I'll first walk you through an outline here of what I'm going to talk about. So I'm going to start talking about instruments and some of the more commonly used instruments for linking optical measurements to flux tower data. Then I'm going to cover footprints, both of the flux tower, but also of what these instruments can see. Then I'm going to talk about ecosystem variability and how this is an important thing to consider when interpreting these data. Speaking of interpreting these data, I'm next going to talk about interpreting spectra, and happy almost Halloween to all of you. And lastly, I'll talk very briefly about how we can use some of this data to help interpret and scale to the satellite. So before we get started, I assume most of you are familiar with these, but I'm just going to throw 5 different vegetation indices at you right now that I'm going to talk about today. The first of which is NDVI, which needs, I think, no further discussion. I will then talk about the near-infrared reflectance of terrestrial vegetation, or NIRV, which basically is NDVI amplified by reflected radiance in the near-infrared. And what this does is it decreases sensitivity to soil background and sort of gives us a wider dynamic range to work with. really emphasizing and amplifying that reflected energy in the near infrared. Then I'll focus on a few more physiologically sensitive vegetation indices, such as solar-induced fluorescence, which is emitted chlorophyll A photons, which are sensitive to shorter and longer term changes in absorbed light by chlorophyll, but also photochemical activity. And I'll talk about the CCI, or the chlorophyll carotenoid index, which was developed more recently to look at longer term changes in pigments and is particularly effective in evergreen forests for looking at, say, sustained thermal energy dissipation driven by the xanthophyll pigments. And then the next one I'll talk about is the photochemical reflectance index, which is more sensitive to short-term or facultative heat dissipation and short-term xanthophyll pigment dynamics and the deepoxidation of those pigments. Great, so let's get started here and first cover some of the instruments that are used on flux towers. So the first most commonly used instruments, and was sort of at the beginning of SpecNet, way before I was involved in the science, are sort of low cost, sort of single or double or triple multi-band photodiode or LED based sensors. The most commonly commercially available ones now are centered around the NDVI wavelengths and the PRI wavelengths shown in the bottom here. The advantages of these systems is that they're low cost, they're easy to deploy and operate, and you can specify different bandpass filters and even make them yourself. The disadvantages is that we do see inner sensor calibration issues, we do have sensor drift, and depending on the bandpass filters you use, you can have a somewhat broad full width half maximum. The next most common instrument would be, I'm calling it a hemispherical, but it's really just a wider field of view instrument that's looking down on a larger portion of the canopy. That can be hyperspectral or multispectral. In this case, I'm showing some diffuser spectra, which would be coming from incoming light, and then reflected radiance from, in this case, a basal leaf, but it could be any bit of vegetation. The advantages of this is that you get more of a canopy average, and it's more comparable to satellite retrievals because you have more vegetation itself. You have a higher signal to noise ratio, but a lot of interpretation of the data is dependent on how you initially set up that field of view. And it makes it difficult to interpret different sun shade fractions on the canopy or different angular issues. And it's more subject to background noise, which is the same as the satellite. So maybe that's a good thing because it helps us interpret the satellite data. Next type of instrument is a scanning hyperspectral instrument. Our group's been working a lot with photospec, which the paper is Grossman et al. 2018 that describes the instrument, but it's a scanning instrument that has a motor in the azimuth and the zenith angles, and it moves around the canopy, and we can specify individual species, like in Zoe Perrot's paper this year, where she looked at spring onset in spruce and larch. We can also set up different scanning patterns to look at angular impacts. So in this case, we set it up to look at 3 different angles, doing these sort of elevation scans with the instrument. So this helps us separate species and pure vegetation spectra from the ground. It helps us better interpret when sun and shade was on a canopy, and gives us more insight into BRDF and angular issues. Disadvantages is that it doesn't have a hemispherical view, so it makes it more difficult to compare to satellite data. And so our canopy averages can be biased towards how our scanning routine is set up. Of course, these are also more expensive and take more development time and care to maintain. The next thing you can do to aid in interpretation of this scanning data, and this is a figure made by Devin McGew in my lab. And what we did is we connected basically a security camera, and I believe Taylor Jones talks about his design here, and ours is very similar to that, where we then put a telescope on the top and we co-locate the retrieval itself with the image. So in this case, you can see Chris Wong taking some field measurements. We're collecting soil spectra here. And so the center of this target is basically the data we're collecting at that given point. And then there also are some multi or hyperspectral imaging sensors out there, which are great for separating soil, vegetation, species, and it's an imager, so it helps in interpretation. You get pixelated information. Of course, you get some distortion with hyperspectral imagery. Calibration can be an issue. You want to make sure that you either are able to collect sky spectra with a target in the field or a reference. And then you also produce high data volume with these sensors. And I'm not going to get into it in detail, but some of the talks today might. Retrievals and calibrations matter a lot, especially with SIF. And if you look at all the different SIF measurements out there and different tower setups and how the retrievals are done, how the calibration's done, how the error is quantified, all these things can lead to pretty different numbers. And this is an important thing to consider when using tower spectra going forward. And that's all I'll say on that, but this is an important topic. Next is footprints. So of course, each instrument itself has its own footprint, as I just mentioned. A scanning instrument might have a smaller field of view looking at individual species, whereas a more hemispherical instrument might just have a fixed, wider field of view. So not only do these instruments have their own footprints, but the CO2 flux data do as well, as many of you know. And so if we're trying to link these optical tower data to a flux tower, we need to consider the footprint of that flux tower. So there's a really nice paper led by Husen Chu last year, which looks at footprint variability at a bunch of different towers within the Ameriflux network. And what they show is that footprint variability varies on many things, depending on the site, the tower height, the wind direction, the surface roughness, tons of other things. So how can we best match optical measurements with ecosystem fluxes? And so I would suggest going forward that people do footprint modeling to figure out where a lot of that flux measurement is coming from and how well the optical measurements align with that. So on the top here is just a footprint model that Erica Orcutt in my lab made at a site in Alaska. And the greener colors are where there's more weight. That's where the flux tower is located. And it has a big contour. I think this is like an 85th percentile contour of where the footprint is coming from. So if you're looking at airborne data that might cover different parts of that footprint, you might ask yourself, how can I best compare airborne data to where the flux is coming from? And so if you just do a simple radius here on the bottom right of 100 to 200 to 50 meters, in this case, across the entire Arctic boreal domain, I think this was like 20 different towers, we don't see much variability in the NDVI signal. But when you begin to consider the contour, say the 85th percentile contour or the weighted average, we do begin to see differences in the data. And this is especially pronounced in SIF data and in ecosystems where you don't have a very homogeneous system around the flux tower. In theory, we hope that that's the case, but in reality, we can't always do that. So next, this is some data that we published last year, led by Lee and He, and this is photospec scanning hyperspectral data from a soybean field. And on the y-axis here, I have viewing zenith angle plotted. The x-axis here is day of year. And so basically what we did here is we did these elevation scans where we go from basically nadir all the way out to 45 degrees. So nadir would be -90 and -45 would be at a 45-degree angle. And so as you can see, I have it colored by NDVI. You begin to see these rows fill in, which is really cool early in the season. And then as the canopy begins more closed, you get this consistent NDVI value. And so this is why your leaf level NDVI data early in the season might look quite a bit different than your canopy data, because we're averaging a bunch of soil spectra into these data, and the black dots here are the canopy average, and you can see the NDVI increase throughout the season. Then I have SIF plotted on the bottom here, and this is just to show that the SIF signal itself is much more variable, and in this case, it's mostly driven by clouds and incoming irradiation. Again, as you know, this is a more dynamic signal than a signal like NDVI. Another cool thing we can do with scanning hyperspectral instruments is understand how viewing and solar geometries impact the data. So this is a figure made by Zoe Perrott at that site in Saskatchewan that I mentioned earlier, where we have 3 scans that go out and repeat every half hour, going out in sort of different directions. And what you see if you just look at the PRI and the SIF data here under direct sunlight on the left and diffuse on the right, under direct sunlight, we see a pretty big difference in the timing of the peak of these data. But there are ways to correct for this. And one of the ways we've been doing this is to compute a relative SIF, which is just taking that SIF value divided by the reflected light within the retrieval window of the SIF data itself. And what we tend to see is much more flat data throughout the day, which makes sense because a fluorescence yield, once normalized for light, should be fairly flat throughout the day. It's really throughout the season where we see these big changes in relative SIF and how we can interpret dynamics in fluorescence yield. That being said, I think there's still a lot of powerful information in the SIF signal itself because incoming light is, of course, one of the main drivers of photosynthesis. So next, let's talk about ecosystem variability. I'm just going to touch on this briefly. And so I sort of drew this conceptual figure here. And in this figure, we're just looking at reflectance of vegetation. We're not looking at the pixel in these pixel in this case, but just vegetation itself. So on the bottom, I have APAR plotted in black, NDVI, NIRV, CCI, and SIF. And if we were just to look at the vegetation and say a grassland or a wetland ecosystem, we see this sort of broad seasonality and these greenness indices. We see that SIF is more dynamic and probably sensitive to how APAR is changing. Similar story for crops, similar story for deciduous species. It's important to note that in both these ecosystems, often, not always, often, APAR co-varies with how much light is being reflected by vegetation and how green that vegetation is. So it makes sense that something like NIRV or NDVI would work quite well in these ecosystems. It's when we go to evergreen ecosystems or the tropics or where we have more trouble. And in many cases, if you just look at the vegetation, your NDVI or your NRV signal might be fairly flat throughout the season. Meanwhile, something like SIF or a pigment sensitive indice like CCI might show more of a seasonal trajectory. The other things we need to consider when looking at canopy structure are, as that photon leaves the sun and reaches the canopy, a lot of things happen to it. But then once it reaches the canopy itself, each canopy has different light absorption profiles, which are driven a lot by the structure of the canopy. And if there's standing water in, say, a wetland, a lot of that near infrared reflectance will be absorbed, and that'll change our interpretation of something like NIRV or NDVI. Once that photon's in the canopy, it's going to bounce around and scattered within the canopy itself, and that can be driven by wilting and flushing and even understory phenology. So these are all things that we need to consider. Ultimately, then we need to come up with algorithmic solutions to account for this and think about how the escape fraction of these photons can basically be used to interpret satellite data. Okay, next we'll get into interpreting spectra, and I'm going to go through a few case studies here. The first of which I think is the power of looking at hyperspectral data from optical towers, is that we can go beyond all these empirical regression plots and we can really understand the biophysical drivers of these changes. And so what Ray Chang did here in a paper we published last year is use data from Niwot Ridge in Colorado. And this is just a mean spectrum average during the growing season in black, and during the winter, when the ecosystem is dormant in red, we can see these. The most pronounced changes are occurring around these carotenoid absorption features, around 531 to 550 nanometers. And the next thing we did was we used an independent component analysis, which is a spectral decomposition method, to compare where the most prominent changes in these spectral features are and what they're relating to biophysically. So we overlaid here some chlorophyll Jacobians and some carotenoid features into these first and second spectral components, showing that changes in, say, the red and blue parts of the spectrum are more sensitive to chlorophyll, whereas these changes in the more yellowish to greenish part of the spectrum are related to carotenoids. And then you can also use techniques which a lot of people have been publishing on the leaf level, such as partial least squares regression, to basically take all of the information from the spectra and compare it to your variable of interest, in this case, Tower GPP, and we see a pretty strong correlation with reconstructed GPP using a partial least squares regression analysis. Notably, it doesn't necessarily outperform, if you look at this paper, things like CCI or even SIF in this case, but still a powerful tool for interpretation. I love tower data because we can look at these seasonal trajectories, and this is a paper from a paper in review right now led by Zoe Parat. We have 2 years of data showing GPP in black and each indice in the color, and you can see these more physiologically sensitive indices in an evergreen forest track GPP quite well. And of course, there are intricacies here, which we talk about more in this paper. Things like PRI and NIRV and NDVI are quite sensitive to winter snow. And so there's no snow filter applied here at all. And so you can see we have quite noisy data in the winter, and then actually a fairly flat signal with something like NIRV and NDVI during the season, albeit some of this variability is driven by the few larches that are in this ecosystem. Next, this is some data from one of our sites in Alaska, just looking at diurnal variability of a few different vegetation indices. In theory, some of these more greenness-based indices like NDVI and NIRV should be pretty flat throughout the day, but we do see, of course, these changes throughout the season, which are highlighted by the different colors. Something like PRI, we might see more of a dip in the middle of the day, which is related to that xanthophyll cycle deepoxidation. Some of this data early and late in the early morning, late evening is of course driven by really low solar zenith angles. So it makes this data more difficult to interpret. But what I like about looking at this diurnal data is it really helps us understand satellite data during a satellite overpass time at say 1:30 in the afternoon in this case. Another thing you can do is look at short-term stresses. So this is an experiment we've been running for 2 years now in a vineyard in Central California. And so it has 4 flux towers situated around this tower, all in different treatments. And what we can begin to look at is how these different towers, identified as RIP 1, 2, 3, and 4, vary throughout the season. And then compare it to something like NDVI, which is fairly flat over this 2-month period, or something like PRI, which shows a lot more variability. The trick with PRI over longer timescales is that, remember, this is an indice that's more sensitive to short-term changes in xanthophyll pigment dynamics. So longer-term changes are often confounded by changes in canopy structure or longer-term changes in constitutive pigments. So what Chris did in this paper is he detrended the PRI signal. So he took this sort of steady state or the seasonal average and detrended it over each one of these stress events. So we had stress 1, 2, 3, and 4. And ultimately what he creates here is a detrended PRI signal to give us an idea of short-term stress response. And it responds really well over each one of these 4 stress events to changes in GPP, where we see these dips in the middle of these stress events. And the PRI data, these are solar noon daily averages that we're showing here, also correspond really well. And then you can take this a step further, and more people are doing this now, and you can do like a random forest analysis. And I won't get into this in detail, but you can ultimately begin to predict over the full observation period or different stress events, what is driving these changes in GPP or in, say, a PRI or an NDVI signal. And it gives us more mechanistic explanation for what's happening and what could be driving these signals. Okay, next we'll get to scaling to space, and I'm just going to cover this briefly because it's a huge topic. But basically, we're talking about going from small individual footprint level retrievals to, say, a more hemispherical, wider field of view, to, say, a pixel that incorporates a lot more information. And so overlaid on that hypothetical figure I showed you earlier, I have dashed lines here. And the main take-home message here is just that, like, let's say there's standing water maybe throughout the season in this grassland ecosystem. What we're going to see is a much more subtle signal, because a lot of that near-infrared radiation is absorbed by the water, by the standing water. However, if we have a fairly dense canopy with a fairly homogeneous pixel in these like cropping or deciduous forest systems, we might see fairly close correspondence between the plant reflectance and the pixel reflectance. Whereas in evergreen forests, oftentimes people observe these changes in NDVI and NIRV, but we have to remember that these seasonal changes are often driven by what's in the background or in the understory. And so Snow can confound these seasonal signals a lot. One of the beautiful things about SIF is that it's just coming from the photosystems themselves. So we know that's just a plant-based signal, although we do have some issues with background that I won't get into. But the point is that if you see a seasonal cycle in some vegetation indices where there is a lot of snow or a lot of understory activity, it might not be representing what's happening with the dominant vegetation and GPP. So Andy McGuire led a nice paper this year, looking at scaling from the airborne vegetation indices to satellite vegetation indices and see how these things vary across space. And this is just data from the AVRIS NG hyperspectral airborne imager and chlorophyll fluorescence imaging spectrometer. And basically the whole point I want to make here is that things change a lot when scaling from tiny airborne pixels up to the satellite because of all the reasons I've already mentioned. And so if we just look at all these different ecosystems on the y-axis and how these and their distribution for a given area where we had satellite and aircraft overlap, we do see quite a big difference in, say, CCI, NIRV, and SIF data across ecosystems. And I think this type of work is really valuable for our interpretation of satellite data. So that's all I have to say. I guess my final points are that a big challenge for SpecNet going forward is to consider all these different instruments. They all have different retrievals, calibrations, and observation strategies. And if you're an end user of these data, it's important to understand these nuances. And if you're producing these data, it's important to document these nuances. Footprints matter, both the footprints of the instrument and the footprints of where your fluxes are coming from. These need to be considered. When you're scaling to space, I think the tower data really helps our interpretation of the satellite overpass time, but also the seasonal trajectory of these data. The tower data can help separate vegetation from background pixels and improve our interpretation of these data. Ecosystem signals vary a lot due to canopy structure and background, and they'll change seasonally. And so just because something works well in one ecosystem doesn't mean it's going to work well in the other. And that gets me to my final point here, which is that I don't think there's been sort of this race to have like a vegetation indice to rule them all. Well, many of these indices have advantages and disadvantages in different ecosystems. So perhaps we need to think about an approach, if we're interested in a variable like GPP, that uses the best information from different vegetation indices to best interpret what's going on across these different ecosystems. And I just don't necessarily think there's a one size fits all approach. And so we don't need to be making overarching conclusions from one small scale study in one ecosystem, and really think harder about how to interpret these data. So when linking all optical signals at the flux tower scale to ecosystem carbon, fluxes, all these things I just mentioned, plus many more that I can't get into and I'm already over time, need to be considered. This is especially important for using tower spectral data for model, satellite, CalVal activities. And that was a lot of information. And I apologize in advance for that, but thank you for your attention. And hopefully we'll see you all soon. Bye.
Well, one of the challenges of running a meeting like this is that you can't stop you can't tell someone they've got 2 minutes when they're recorded. So, just really quick, are there any, I don't see any questions in the chat about this. Zoe, Erica, Chris, I know are all there. There might be some others from Troy's lab. So if there's any quick questions, I don't see anything. Otherwise, so we're running late anyway, so I guess we will move on. The next thing is Gabriella Shirky. Is she here? She's to do a poster. She's a PhD candidate from Michigan State and an organizing member of the FluxNet Early Career Scientist Network. And her poster's on simultaneous measurement of leaf gas exchange and water content.
Actually, that was a little bit of a mistake in the agenda. So I'll be talking about GPP estimated by flux towers, and then how we're creating those through other satellites.
Please go.
Okay, cool. So sharing a poster virtually is always fun for everyone. I'm going to go ahead and start sharing my screen here. Let's see. I think it's this one. Okay. All right, so hopefully everyone can see this. Sorry, I was muted there. Thank you.
Yes,
Thank you for
yes,
that.
we can see a very tiny poster.
It's going to be a very tiny poster. So the way that we can navigate through this is that I will give you a brief introduction really quick verbally, and then I'll scroll in and go through each of these sections. So yeah, thank you again, everyone here for having me. My name is Gabriela Shirky, and today I'm going to be talking about modeling of gross primary production within agricultural grassland landscapes. And the reason that I'm interested in this is that growing up in Michigan, I noticed that we have a lot of tiny little plots of agricultural area. And then when I began my studies in geography, we're using quite coarse resolution to estimate gross primary production across the landscape, right? So a lot of these agricultural sites that we have are just not as big as multiple pixels of 500 meters squared. And so when I wanted to understand carbon fluxes in a landscape, contributions to global warming, et cetera, I had to say, wait, we have small patches of agricultural land that are speckled with forest land in between. And if we use too coarse of a resolution to estimate those patches, then we might be over or underestimating GPP. So with that brief introduction, I'm going to go ahead and try and scroll in here as best as I can. And how do I make my bar go away? Wow, did that all get, well, I apologize for that. Somehow it's been converted into hieroglyphics or something. Okay. Here's my backup then. I have a backup option. All right, so this one won't be as navigatable, but we'll go with what we got, right? So in the estimation of GPP, I've selected to use a popular model, the vegetation photosynthesis model. And I built it with various resolutions. So I have a Sentinel-2 with a 5 meter, Landsat-8 with a 30 meter, and then our typical MODIS product with the 500 meter. Just for fun, I did look at what that looks like in the Landsat CONUS product, which is also 30 meter, and then the conventional Mod 17A2. So unfortunately, I won't be able to scroll down super well. This is going to be a little bit of a shorter presentation, which is fine. So our study sites, as you can see, we have a map down here, right? So each of these red colors, orange colors, green colors, that's to say that we have replicate plots. So in our study sites, we have 7 managed agricultural grassland ecosystems. 4 of them are on previous USDA Conservation Reserve Program that was recently converted back in 2009. And then on the other 3, we have conventionally farmed land. So I'm calling that AGR for agriculture. So until 2009, it was cultivated with corn, soybean, wheat, and then transitioned into what it is today. So we have our sites that are now a no-till corn, native prairie, and a switchgrass. And then the sites that are planted on traditionally farmed land include a no-till corn, a switchgrass, and a native prairie, as well as a historically preserved CRP land. So we do have a reference site. That site has stayed a CRP land since it was acquired by the Kellogg Biological Station. Right, and here we can scroll in a little better so that folks can read if possible. So our study site is located in Southwest Michigan. Our study period is March through November 2018 and 29. And then we're just going to compare the performance of each model with tower-based estimates and a simple linear regression. But a question that I was really curious about is whether these sites have any sort of significant difference between them, or if they have a significant difference between satellites as well. So for those who are unfamiliar with the vegetation photosynthesis model, you can see that it includes 4 parameters. We have the maximum land use, light use efficiency, which we calculated for each site, the effect of temperature on vegetation photosynthesis, as well as the effect of water on photosynthesis, which is represented by the maximum land surface water index, right? As well as the effect of phenology. We used typical products here. I can't scroll, that's great. Landsat CONUS, which I want to note is great because it does use biome-specific light use efficiency, whereas the classic MODIS GPP product, which a lot of us like to use, has a more generic lookup table. And then we estimated tower-based GPP and our EDI-PROC system and did appropriate QA/QC on that, right? So looking through at the results here, you can see what a time series of each of these GPP models have looked like. So again, AGR does stand for the historical agricultural sites, and then CRP will stand for our recently converted conservation reserve program sites. And this black line is our tower estimate, and then we're just comparing and looking, right, to see where everybody else is kind of falling on this graph. And what I've been noticing so far is that our higher resolution data is capturing this peak growing season information, sometimes even overestimating it, which could be due to any sort of disturbance on the site. We did select our pixel information offset a little bit from the tower, so it didn't include any sort of disturbance. So I'm curious if the higher the resolution we select for a GPP model, the more likely we're going to see that in-field variation kind of crop up, no pun intended. And then we start to look at what more of the coarser resolution looks like, and then any sort of classic model that we might have. So the MODIS product, the conventional MODIS product is this blue here, and it hasn't been performing as well. And so I'm starting to think again, like that could be because of the adjacent land cover types that are being incorporated into its analysis, as well as that Landsat 8. We took the next step down here. You can compare this table if you are a table person. Tables are not really attractive, I understand. So we do have a one-to-one regression here just to see which of these models were typically performing similarly as tower-based estimates, right? And we can see that by and large, many of them were underperforming. And again, that has to do with that peak growing season period. If I were to color code this into spring, fall, and then our summer period, you'd see that spring and fall, which typically have lower GBP estimates, are more on the one-to-one line. So again, we're seeing a little bit more underestimation here with classic MODIS products and a more one-to-one relationship with our higher resolution products, right? And so to get to kind of the question that I had was, this is all quite new to me as well here. We're looking at now any sort of differences that might be between sites. So the way to read this would be, this is from our post hoc 2D test. So for each little facet rep here, each little site, so agricultural corn, we would look at our letters and see if there is any similarities or significances. So for example, in agricultural corn, we are seeing that MODIS and Landsat 8 VPMs are somewhat similar. They are not significantly different, but we are seeing a significant difference in Sentinel-2. Correspondingly, we're looking at whether that's the same in a historical CRP site as well. So again, this kind of brings the question forward: how does land use history impact our GPP estimates? Like, are we paying attention to that when we're getting landscape analyses? Down here, this is unfortunately a little squished. So what you'll see is BC here, and then AB. That should be wrapped around, but exporting. So what we're looking at here now is, for each site, are we finding a significant difference between the sites? For each satellite, is there a difference between each site? So what we have are AB and AB, right? So there's not a significant difference here between our reference plots and then our CRP, our conservation reserve converted to switchgrass. But there is a significant difference between other sites, including corn and our prairie. Whereas what's interesting, there's no significant difference between sites when we're looking at them just with an Sentinel-2 VPM or with an LS8, Landsat 8 VPM. So those are the outcomes of this. And the reason that I wanted to bring this to the community here is to see what are your experiences, especially working with different satellite products, different resolutions, and how that might affect your own estimates of GBP. So, thank you very much for your time and for your patience with our poster presentation virtually. I appreciate it. Thank you.
Well, thank you, Gabriel, for at least being a guinea pig for the poster presentation here.
I was a guinea pig, wasn't I?
So if there's any questions for Gabriella.
Gabriella, yes.
Thank you. I'm sorry.
I have a bit of a comment and maybe not so much a question. Thanks for your poster. It's a nice study. And I think it's remarkable how well MODIS works in some cases. It's coarse resolution, but it's quality data, and it has, you know, spectral bands. I guess, do you have any sense of that yourself about, you know, these different satellites? My sense is that the MODIS products, sometimes, depending on which ones you use, are outstanding, and that provides certain benefits that you know, despite the resolution or other issues. But those we've seen that in some places. Do you have any thoughts on that?
Yeah, and again, this is what's really important to me, because I'm seeing that in my MODIS VPM, it's not performing really great, right? But I know that our community uses it and relies on it and has found many times that it's fantastic. So in my construction of this, I just noticed that the EVI is very low. And so I don't know if that has to do anything in particular with my location, or again, the coarseness of its resolution on my landscape study. But that, I believe, is what's creating this very low GBP estimate. Because comparatively, if I was to look at my EVI estimates that are going into this model with another VPM study, perhaps, those are quite different, right? And so we did our due diligence of pulling it from different sources, having multiple people come to the same conclusion. So comparing this product to other products might be useful, but it does come with that, you know, other side of the story, right? But I do believe that we're having pretty good success with Landsat 8 as well as Sentinel-2 and kind of addressing that more constrained sample.
Thank you.
Well, thank you. And I want to thank all of the speakers in this session. And now we're going to move to breakout groups and discussions. So take it away, John, Gilberto.
Oh, yeah. So
Yes.
I think, Gilberto, do you want to comment on where we are in the process of breakout groups? And I can fill in if you need time, but go ahead.
Yeah, absolutely. So just before we jump to that, I wanted to take 2 minutes to do a quick activity here. Can we take a group picture? So this should be really quick. So everyone who's comfortable with turning on your cameras, please do. And I will do a quick screen grab here. So just we have a little bit of a record of the meeting, and you please be a little patient here. There are only so many people that can fit on a screen. So let's go for the first screen here. So say cheese.
Cheese.
All right, so now for the second round here, say cheese again. All right, and just one more. We have just one more screen here. So one last time, say cheese. All right, awesome. Thank you, everyone. So for this portion, we have the little poll that that we shared. I'm going to just paste the link here again quickly, just so if anyone wants to have a last minute addition to that, please do. And I'm going to show you what we have so far here. Give me just a second. So here we go. So we had the some of the original entries that we had added. There is quite a bit of interest for those sessions. And we had one more here that was contributed. So I think what we'll do is create a breakout room for all of these. And what I'll also do is add a few extra rooms without necessarily an assigned theme. So if you want to chat with someone specific and didn't have a chance, I know that in these meetings we get to see so many people that we haven't met in such a long time. So I'll leave those additional rooms open as well. But if anyone has another suggestion of an additional breakout room, maybe one of the speakers want to take in more questions or something like that, please let me know and I will assign these. So if you give me just a minute here to start the breakout rooms. John, I don't know if you wanted to take over for a little bit. I need just a couple of minutes here to create these rooms.
Sure, thanks, Gilberto. You know, first of all, I want to thank everybody for their contributions. It's been a great meeting. We were not sure how this was going to work. We're breaking new ground having this kind of a meeting. And I have to say, Gilberto's doing a great job. So we need to give him a hand for that. But everybody did really well with this. We're really interested in your feedback on this format. I mean, we thought about this pre-COVID, about the idea of having virtual meetings so we didn't have to fly around and meet. We used to meet at AGU, and most European colleagues and people from other countries couldn't often come. And this is fabulous in terms of the participation, but then there's new challenges as well. For example, you know, it's a different kind of experience and the interactions are different. So we're trying really hard to figure out ways to make this work. The breakout rooms will be some. And, you know, I look forward to that. But just a few comments is I want to comment on, you know, these have been some great talks. We've seen some good explication of different SpecNet themes today. And it strikes me that, you know, a lot of these themes haven't changed that much. The basic concepts behind what we're doing haven't changed that much. The technology has changed a lot, but we're getting a lot better understanding of these things over time. And, you know, there's always the same challenges, like the issue of you know, standardization always comes up. And as Troy points out, you know, it's not just technical standardization, there's issues of ecosystems that come to bear on these kinds of questions. So it's, you know, it's where biology meets physics is a complicated place. And I think we're sort of seeing that in these talks today. And anyway, I wanted to thank you for your participation, your ability to you know, put up with the format. And thanks, Gilberto, for doing a great job keeping us going.
All right, great. So we are ready with the breakout rooms. I'm just going to get them started. So the rooms are created. You can access the breakout room menu at the bottom of the Zoom interface. There is the little squares there. If you don't see it, it might be under the 3 dots at the bottom with additional options. So if you just open the breakout rooms, you're able to see all the rooms that are available, and you can just hover over the name of that room and click join. And we will have these open for about 30 minutes, and I'll send a note to everyone when we are 10 and 5 minutes out. And if anyone has any trouble getting into one of the rooms, please let me know. I'll stay here in the main room and make sure that everyone gets to access the breakout rooms.
Gilberto, do you want to say a little bit about how much time we're going to spend doing this, and then?
Yes, so we have 40 minutes assigned for the whole session. We are about 10 minutes in, so I suggest a 30-minute time for the breakouts. And you don't have to stay the whole time in a single room. You can jump through the rooms that interest you, yeah. And if you want to come back and hang out at the main room as well, you can always chat here too. And if you have an additional breakout that you want to start, let me know, and I'll assign one of the extra rooms that are available there. Is anyone having any trouble getting to the rooms? Need any help? I can also help you get into one of the rooms if you like. Just speak up. You can unmute yourself or send me a note on chat.
Sorry, Gabriel. So where we enter into the room, there's some link or?
Yes, so in the Zoom interface, there is a breakout rooms icon. So if you just click on that, or you can tell me which room you'd like to go into and I can get you there.
I think because I choose two, but maybe first for the, I think the fluxes with spectral measurements.
Yeah. Okay. Connection between covariance and spectral measurements. Okay, yes. I can get you there.
Okay, thanks, Mark.
It'll take a second.
Thank you.
If anyone else is having trouble getting to one of the rooms, let me know.
I'm having trouble getting to it. I chose one or navigated to one I thought, but I'm not getting to it. I'm not sure why.
Which one you wanted to?
I think it was the first one, networking opportunities.
Okay, I'll get you there.
Not
you will see
a key step. Yeah, okay.
All right, and anyone else needs a little help getting into one of the rooms?